Dr. Vishwaji sir, you can start. Okay.
Okay. Uh, Good evening, everyone, especially Professor Dr. Jyotsna Kumar sir, because we are very much privileged and honored that he is accept our invitation and agree to deliver a lecture in this platform. So, formally to introduce all, actually, good evening, everyone. It is my pleasure to welcome you all to the day 5 of this AICT sponsored 6-day online AICT Teaching and Learning Faculty Development Program on Advances in Material Science for Sustainable Development and Industrial Application, organized by Department of Basic Science and Humanities, Dr. Sudhir Chandra Sur, Institute of Technology and Sports Complex, Kolkata. As we step into the 5th day of this enrichment journey, I would like to extend my heartfelt gratitude to all the esteemed speakers for their valuable insight and to all participants for their active engagement and participation. Over the past 5 days, we have explored cutting edge advancement, research trends, and industrial application that align with the sustainable development goals. And we just left only 2 days, and today we have two sessions. Session 9 with Professor Jyotsna Kumar Mandal sir. He is from Department of CSC, University of Kolkata, and his title is Role of Alternative of Silicon for the Designing of Semiconductor Devices and Circuits. And the next session, session 10, with Dr. Subarna Shyamroy. He is General Manager R&T, Head of Emulsion Asian Paints, and his title of talk Sustainable Materials and Chemistries for Coating and Industry. So with that, so now I am requesting the Dr. Dipankar Das, HOD, Department of Basic Science. Sir, please introduce Jyotsna sir to all of us participants.
Okay. Thank you, sir. Good evening to all respected speaker, Professor Jyotsna Kumar Mandal sir, and also all the respected participants. So now I am going to read a short bio sketch of Professor Jyotsna Kumar Mandal. So Dr. Jyotsna Kumar Mandal, MTech in Computer Science from the University of Calcutta in 1987. Awarded PhD in Engineering in Computer Science and Engineering by Jadavpur University in 2000. Working as a Professor of Computer Science and Engineering, University of Kolkata. Former Vice Chancellor, Raiganj University, West Bengal. Former Dean, Faculty of Engineering, Technology and Management, KU, for 2 consecutive terms during 2008 to 2012. Former Director, IQAC and Chairman, CIRM, Kolkata University. Served as Professor, Computer Applications, Kolkata Government Engineering College for 2 years. He was Associate Professor in Computer Science for 8 years at North Bengal University and Assistant Professor in Computer Science at North Bengal University for 7 years. He also served as lecturer at NER IST, Itanagar for 1 year. 36 years of teaching and research experience in coding theory, data and network security, and authentications, remote sensing, and GIS-based applications, data compression, error correction, visual cryptography, and steganography. Awarded 31 PhD degree and 4 are pursuing. He supervised 3 MPhil and more than 80 MTech and more than 130 MCA dissertations. published more than 450 research articles. Recently, he has published a textbook on reversible steganography and authentication via transform encoding from Spinger. This book has been translated into Chinese language and republished from China by the Spinger. He has organized more than 65 international conferences and corresponding editors for volumes and conference publication of Spinger, IEEE, elsewhere, etc. He edited 65 volumes as a volume editor. Received Shiksha Ratna Award from Government of West Bengal, India for outstanding teaching and research work in 2018. A.M. Bose Memorial Silver Medal and Kari Prasanna Dasgupta Memorial Silver Medal from Jadavpur University. Vidyasagar Award from International Society for Science Technology in 2018. Research Icon Award from University of Engineering and Management, Kolkata in 2023, and Academic Excellence Award from University of Engineering and Management, Kolkata in 2024. Highest 220 Scopus-based publication in last 10 years among all faculty members of the University of Kalyani. ISO World Convener of ISO IEC JTC 1/SC36 WJ7, Governing Council member of ITE India, Eastern Zonal Mentor of IEPE New Delhi. So this is the short sketch, bio sketch of Professor Jyotsna Kumar Mandal. So now I would like to Professor Jyotsna Kumar Mandal, over to you. So you can go ahead.
Thank you very much for giving me opportunity to interact with all of the participants and giving me the opportunity to share my thoughts and our lab works of my scholars and my research work to the participants. So my today's topic is role of the alternatives of silicon for the design of semiconductor devices and circuits. So prior to that, I would like to go for some background of this study so that everyone can understand that how we are proceeding and what are the latest. So you see 75 years of semiconductor has already passed. So already passed and now we are just at the age of nanoscale device and modeling of nanoscale devices. And secondly, Government of India giving a major thrust on hardware-based fabrication. Because you see, still now, I think that our fabrication technology is, I think, still 160 nanometer to 180 nanometers, Chandigarh and Bangalore. And you see that it has been boosted up to 20 nanometer in the next 5 years. Still, we will be lagging. Still, we will be lagging because you see that now the research and Intel has already, I think, published the device with 10 nanometer gate length. So first, I will go the journey of the 75 years of semiconductor device. Then we shall go for design of various nanoscale device. Our device mainly consisting of 10 to 4 nanometer. Mostly latest design, and all of these articles are published in good ACI journals and others. And we have used some alternative materials, and we have chosen various materials other than silicon. So this is my journey of today's lecture. So let us go that in the timeline. So in 1904, so two electrode vacuum tube was invented by Thomas Alva Edison, and that was the beginning of the mobility of electron through a device. And that this is the picture of the device that we are showing here. Then in 1946, the first general purpose computer ENIAC was announced. You see, this is the picture of that computer. You see that journey of that particularly. Then in 1948, Johnson type transistor is invented by William Schottky. And another thing you will be astonished that in 1901 or 1902, the solid state device was proposed by Sir Acharya Jagadish Chandra Bose. And you see that vacuum tube persists till 1949. And after 1949, we have extensively used the solid state devices. And that is why we used to say that our Jagadish Chandra Bose is always 50 years ahead of the time, because he was invented the microwave, millimeter wave in 1901, it was patented. And also you see in wireless communications in 1895, he had demonstrated one experiment in town hall at Kolkata, where through wireless communication he has exploded a gunpowder kept outside the hall and a calling bell remotely. You see that our Kolkata is a pioneer of these sorts of things. So in 1948, the junction type transistor is invented by William Shockley. Next, you see that in 1955, so earlier was year 1948. Then you see after almost 8 to 10 years, the Japan's first transistor radio, the first transistor is released by Tokyo Telecommunication Engineering, now which is called the Sony. The name was converted to Sony now, but it was done by Tokyo Telecommunication Engineering Corporation. It was in 1955. You see, this is your Sony, and you see 1957 Ekasi diode was invented by Leo Esaki, and it was I think patented by Sony. And you see this is this picture. Now in Kilby patent was filed, which refers the basic concept of integrated circuit, and developed by Jack Kilby at Texas Instrument. You see, this was the first fabrication of the ICs. That means the concept of transistor and the integration of transistor in a different way, that has come to a single wafer as an IC. It was done by Kilby. So then in 1965, you see, almost 60 years after the invention of the transistor, you see that vacuum tube, Moore's law is announced by the Gordon Moore. According to the Moore's law, you see that started from 1970 to 2015 around. You see that 1970 to 1980, the count of the transistor is the green line. You see, and the design rule and the length of the gate and the dimension is reducing drastically. And there is a crossover around 1995. And now you see, we are still ahead of that. So after 2025 or 30, so this Moore's law is very difficult to satisfy, because a lot of other effects are there. Still we are down slicing. Nowadays, at the state of the art, we are talking about the down slicing of less than 10 nanometer, which I will talk in details today. So that is the always the integration capacity is doubled and gate length is half. Quite the interesting. And so in 1971, Intel 4004 IC was released. It was world's first single chip microprocessor. Then you see, this is another evolution. And it comes in 1971, where the Intel 404 was released as a single chip microprocessor. That means everything is on chip. Nowadays, we are talking about a mixed signal processing. We are in the arena of mixed signal processing. So in 1977, world's first personal computer Apple II was announced. In 1977. Then in 1980, the first kind of flash memory was invented, which is rewritable, non-volatile semiconductor memory device. We know all of our computers we are using as a concept of stored program. So in stored program concept, you see, we have to keep our data, information, instruction into the memory. So to keep the instructions and all other permanently, fast drive memory was invented is 1980. In 1983, the family computer Nintendo, a video game console fitted with a 8-bit CPU, that was released. You see, this another direction was emerged in 1983. Then in 1991, carbon nanotube was discovered, and nowadays again the development of the carbon nanotube is extensively being used for various communication techniques and other. In 1993, first practical blue LED developed by Suji Nakamura. And that again give a revolution of the lighting technology. Because if you can mix all RGB, then enormous number of colors we can, you see, generate. And that is why you can see the beautiful lights nowadays. In 1995, Sharp released the liquid crystal display TV. Now you see normal transistor, then normal monitor, then it has converted to liquid crystal. So that means array of liquid crystal, we are going for your display device, and it enhances enormous. You see, in around 90 or 89, so when we were working on image processing, at that time it was a normal monitor, and there was two excitation level of the electron. That means either white or black. So we could have only two state, and at that time when we used to process the image, we used to go for only the two level processing, and after that during 92, 93, so we have gone for up to 32 level. Grayscale images were introduced in time, and according to that, the technology of your monitor and the graphics evaluator was discovered and implemented. And then I think, you see, when I have submitted my thesis in 1996-7, you see, I have worked up to 32 gray level with the Lena image. Now you see enormous color image you are using, but we could not do that. Even that, see, nowadays you have thousands of your routines, Python programs and all other programs you have. But at that time, you have to call a separate interrupt. A routine is to just, you have to draw your pixel into the monitor separately by using some calling of the interrupt, which is INT86 interrupt. Most of the cases, that is IO interrupt, INT86 interrupt. If you call, then one pixel can be excited in a particular level. So that level of your programming has gone. Now everyone, we are going for, it is a block level simulations that you call the routine and enormous things will go for your way. And particularly if we use nowadays the Python, that all are inside the routine. But these are normally what, when we have started this work as excitation levels in terms of the image processing, in terms of thus drawing an image into the monitor is the excitation of the electron in terms of the interrupt call, particularly INT186. In 2002, supercomputer Earth simulator was world's first or fastest processing speed of 35.86 teraflops. You see, it was invented. You see, this is the picture of this Earth simulator built by NEC for the Japan Aerospace Exploration Agency. It was Energy Research Institute of the Japan, the science and technology, and fastest computer in the world from 2002 to 2004 around. In 2004, again another direction has opened. Graphene creation experiment proved that successfully by the scientists. So graphene, or an atomic scale sheet of carbon atom. It is atomic scale sheet of carbon atom where we can go for excitation of that, and it's attracting the attention to a high performance semiconductor material. So which can replace the silicon. So two parallel research. One is towards the graphene. So a lot of chemistry people are working on that. A lot of chemical engineers are working on that. And parallelly, we are going for downslicing the semiconductor devices. In 2007, Apple announces the iPhone by Steve Jobs. It was a category of smartphone that has been introduced in 2007. In 2010, Apple announces the iPad. You see, various versions of iPads are there. Then in 2011, K Computer, Japan's supercomputer achieved the world's fastest processing speed of 10 petaflops. K Computer, named from the Japanese word kel, which stands for 10 quadrillion. That is a supercomputer. It is invented by Fujitsu. In 2013, Google Glass beta test starts. You see, from 2013, virtual reality came into play, augmented reality and virtual reality. Now in 2015, Kin Sakamura received the ITU 150 award for IoT. Now another world started from 2015, world of sensor. Now we are in the 11th year of world of sensor. Nowadays, every one of us wearing at least 5 to 10 sensor. In your clock, you have some multiple sensors: gyroscopic sensor, heart monitor sensor, pressure monitor sensor. So all of these IoT devices, you see that miniaturization of the semiconductor industry in terms of the dimension, reduction of the dimension, and increase of the density of fabrication. Enormous advancement gives the IoT devices. That means nowadays we are using sensor-based devices for our sustainable world. You know that UNESCO has declared 17 goals for sustainability across the world. That means how many goals you can achieve. That is that you are going for betterment of your society. So in 2016, AlphaGo AI program. So just 1 year after the IoT devices, in 2016, AlphaGo AI program developed by DeepMind defeated the human world champion in the game of Go. That was in 2016. So the road of the transistor, we can say that the vacuum tube are not suitable for low power consumption, because the operation And for high frequency operation, particularly in the microwave range, and due to difficulty in the size, so it was very difficult to go for vacuum tube for better application. So the idea was to modulate the lateral current in a solid state material by vertical electric field applied to the third terminal, that is grid or gate. So this is the analogy to the triode vacuum tubes. And the idea of field effect transistor evolved from there. So at that time, transistor was not there. But you see that third terminal was used as a grid of the transistor. So it was different from the case of electron current in the vacuum controlling the electron current. So it was assumed to be necessary to use an extremely thin semiconductor film as the solid state material. So first recorded ideas of field effect transistor was patented without any experiment in 1925 for MOSFET and 1928 for the MOSFET. So those semiconductor used for coaxial crystal rectifier. So until 1930, band theory using quantum mechanics, concept of holes and p-n junction, the quality of the semiconductor material was not known much. So during the period 1945 to 48, Shockley of Bell Laboratory thought of an idea of MOSFET independently from previous MOSFET. His idea was to modulate the carrier density at the semiconductor surface by the band bending caused by the vertical electric field. So he has adopted that the use of vertical electric field from the gate electrode. So he predicted the amount of carrier density modulation based on the calculation using the band theory. So band theory was introduced at that time. So the experimental carrier they use on silicon, germanium, and CO2. So it was 3 to 4 magnitude of the order smaller. It was smaller. What was theoretically calculated, it was smaller in practical implementation. So the inversion type of conduction was founded by J. Barden in 1947. And the inversion layer conduction used in the today's MOSFET was clearly described by Brown, and he published the paper in 1953. J. Barden and W. Brattin in December 1947, current application phenomena when put the two gold point contact electrode, emitter and collector, with separation of 50 micrometer directly into the n-type germanium surface. The amplification mechanism were different from the normal FET. And this transistor was later called point to contact bipolar transistor. That means from there we have started the bipolar transistor, because both majority and minority carrier contributes for the amplification. So you see that transistor we are using gradually for the miniaturization, and you use the monolithic integration circuit. It was started in 1958 and 59, and first MOSFET was realized by choosing thermally grown oxide in silicon as gate oxide, and MOSFET was replaced by the BJT in large scale integrated circuit by the end of 1960. Now the minimum line width used for the nano CMOS VLSI about 15 nanometer. The minimum line width was decreased about 10 to the power 5 times. Compare with the first vacuum triode in the past 115 years, and 10 to the power 3.5 times since the first transistor in the first 75 years. You see, these are the interesting point, and miniaturization and downslicing of the size. So because of the size decrease, the performance such as operational speed, energy, power consumption, latency, volume, weight, and cost of electric system and machines improved billion and trillion times. And the invention of transistor, so you see 75 years more than that ago, the device manufacturing, and it was great technological leap. So you can see that the miniaturization of the transistor through a graph. You see, we have come here as the 75 years of age. So, and it is in terms of the operational speed, energy consumption, volume, weight, cost. So, it is a tremendous increase in performance in 115 years. And now electron device size is 10 to the order of -5. So, according to the IEEE IRDS, International Roadmap for Device and Systems 2021, 3 nanometer logic CMOS technology will start production. I think after 2022, I think 10 nanometer has already designed. So the scheme of device miniaturization is continued since the invention of the transistor. So thus, that you see that 3 nanometer is the fundamental limit we are talking about nowadays. In 2021, 22, 23, 24. So we are talking about the 3 nanometer is the limit. It's called the fundamental limit caused by the direct tunneling leakage current, and 0.3 nanometer is the ultimate limit due to the atomic size. So you can see that here. 3 nanometer is the fundamental limit caused by the direct tunneling leakage current, and 0.3 nanometer is the ultimate limit due to the atomic size. So there will be no pico technology after nanotechnology. What the research direction will go, we still not aware about that. Only the researcher can give a new direction. And the end of device miniaturization is not so far. Until and unless some other new technology is introduced. So the progress of integrated circuit with Moore law will continue by the 3D integration. So nowadays 3D integrations are also going on. So the progress of 3D integration will reach a limit in 10 to 20 years because of the increasing heat density and cost increase. However, demand for high performance semiconductor device with low power consumption will keep increasing in future in super intelligent society. Now AI based systems have been evolved. So future intelligent society will create many new business we don't know, such as 6G communications, autonomous driving, everything we are going on. So next leap of the technology will the introduction of the biosystems. So these are some of the references. Now we come to our exact discussion of the role of alternate materials of silicon. So how alternate material takes its role. So already we have discussed, so memory chips are a backbone of your prerequisite for any device and any emerging technologies. So from artificial resilient smartphone, the adoption of IoT and 5G, these are coming up, 6G is coming up. So all IoT devices are made of ICs. So you see, regarding the industry, Taiwan's TSM and South Korea's Samsung Electronics contribute most of the cases 70% of the semiconductor manufacturing market. And TSMC is the top manufacturer of chip at 10 nanometer and below, while Samsung leads the memory chip market. That is, major memory chip market is dominated by Samsung, and the IC manufacturer is Taiwan's TSMC. Intel dominates the market for desktop and laptop CPU. NVIDIA, Qualcomm, Broadcom, Advanced Micro Device, AMD are some of the well-known US companies specialized in chip design. Again, Japan and South Korea companies produces the majority of wafer. You see, each of the company has a specialty for their design. So technology inflation such as 5G, wireless, artificial intelligence, or Internet of Things, cloud computing and machine learning are driving up for a long term of these IC and chip industries. So now, what is the driving trend now? So the industry is stretching the physical limitation of the silicon. So we are towards the end of stretching of the physical limitation in terms of the density of the fabrication, in terms of the minimization of the gate length. So the most common semiconductor material we are using is the Moore's law may no longer apply normally after 2025. So the expiration of Moore's law comes as semiconductor buyers most notably in the field of artificial intelligence. And then we have to focus on the AI-based CMOS design. So when I am talking about the scaling of semiconductor, see, we are going for some investment, market growth is there, we are needing a better performance. So what we are doing? We are going for a lower dimension, we are going for doping, we are going for lower voltage, we are going for integration density, we are decreasing the delay, we are just constraining and we are just limiting the power distribution, and also we are limiting the field effect. So I am not going to the picture. So I think those are the part as this material and others. So I am not going to the circuit part in details. So reducing the critical dimension. That means when the dimension is reached to a critical level, while keeping the electric field constant, one obtained at the same time the higher speed and a reduced power consumption of a digital MOS circuit. So these two parameters become the driving force. So in our algorithmic sense, we can say that the multi-object optimization should be there. That means the AI will play a major role for these circuit simulations. So my things are here, the nanoscale semiconductor devices, some of the devices we have simulated and we have compared with some of the existing materials. Mostly we have gone for single gate and double gate. And here we have gone for metal oxide field effect semiconductor, complementary metal oxide semiconductor field effect transistor, and their challenges. Challenges in terms of downslicing in the physical dimension, challenges of deploying the material as alternatives of silicon, and next is circuit level application. I will show you some encryption techniques. Nowadays you see that on the IC chips, as earlier we used to go for only the digital circuits into an IC. Nowadays we are going for a mixed signal processor into the ICs. That means they can produce everything, analog signal as well as digital signals. Now our aim is to fabricate some security level design into the CMOS gate level circuit where you can use encryption in terms of some interrupt calls and others. I will go for it in details. That is some of the work of our lab. Recently we are doing that work. So why the semiconductors are important to the computer technology? Because it's the ability of the semiconductor material, usually silicon, to act as an insulator or conductor. So due to that reason, so the possibilities of integrated circuits are there, and that is why the integrated circuits are possible. And by adding the impurities to the pure silicon, the semiconductor can be manipulated reliably as an insulator for conductor when exposed to heat or electrical current. And you know that all computer chips are made from semiconductor products. So semiconductor miniaturization makes it possible for the smartphone to have a processing power more than the IBM 1130 or the other computers in the 80s. So, now, according to the literature, you see that first chip in 1965, and you see in Ziauddin highlights the higher leakage current in threshold voltage in the device having lower than 0.1 micrometer channel length. So Almo et al. And Norami et al. highlighted the impact of implantation of high K dielectric. Nowadays, we are talking that if you go for high K dielectric material to overcome the short channel effect with the performance of sub 10 nanometer regime, when we are going below the 10 nanometer range, so short channel effect is a major concern. So for that, so if we use some high K dielectric material, so our design may be effective. Lin et al. Highlighted the advantage of gallium arsenide. You see, we are talking about the alternate material. So Lin et al. Highlighted the advantages of gallium arsenide based material as a channel material in the sub 10 nanometer regime. So my problem domain is go for alternatives of silicon, downslicing of physical and electrical parameter of MOSFET in terms of gate length, channel thickness, etc. Drive current, leakage current, threshold voltage, power. So that means when I am going for a downslicing, so you have to downslicing the gate length, channel thickness, etc. But you see, you have to think of drive current, leakage current, threshold voltage, short channel effect, power. So we are thinking always as a low power device. And again, we are thinking of circuit level applications in terms of designing of sub 10 nanometer ranges. So for this design, we are thinking of aluminium, boron, copper, germanium, gold, lead, phosphorus, silicon, silver, and tin. All of these materials we are thinking of. See, gallium arsenide, indium gallium arsenide, platinum, silicide, and titanium, tungsten, and high-K dielectrics of cadmium, neodymium, and promethium. All of these materials we are thinking of that we can go for high-K electrics. So for the silicon, this is a most common substance on the planet after carbon. Silicons are being used thousands of years. Then the polysilicon is a highly pure and polycrystalline form of silicon used as a conductor and resistor and for MOS gate metallization. Then we are coming into the gallium arsenide. This is a compound semiconductor material made by combining gallium and arsenic. I will show you that gallium arsenide, what is the performance of gallium arsenide when we are simulating that, while capable of operating in the higher temperature than silicon. Gadolinium arsenide is used in semiconductor devices. I think some sounds are there. Someone may please mute it. It's complicated by the toxicity of its compound. This is another problem. Some noise is coming. Can you mute the noise?
Sir, we did it. We did it, sir.
Please, too much noise was there.
Okay, okay. Thank you, sir.
Okay. So, alternatives of silicon and silicon dioxide materials, we have to think of that. So, silicon germanium, indium gallium arsenide, gallium nitride as a semiconductor agent for its peak electron mobility of 2800 centimeter square per volt second and 11200 centimeter square per volt second and 2000 centimeter square volt second respectively. Whereas silicon having only 1000 centimeter square volt per second. You see that here you see gallium arsenide, silicon germanium and gallium arsenide here 11200. If you can compare with the silicon, you see peak electron mobility is a high electron mobility and thermal stability and high switching power than silicon. So these are particularly very effective for 10 nanometer sub-regime. So I think everyone knows that. Say if you go for a metal oxide semiconductor field effect transistor MOSFET, so you see this as we have the silicon normally we are using and we have the structure. I'm not going into the structure. I'm going for the analysis only, analytics. And if you go for various cross sections and perspective sectional views, so you can see all of these things. You see that silicon oxide doping and all other. So normally MOSFET have a NMOS and PMOS. So we have the enhancement mode and depletion mode. So these are the terminal symbols we are using. I am not going into details of these terminal symbols. So how does the enhancement of MOSFET work without a channel? This is where the gate voltage plays a significant role because the gate voltage serves to create the channel in enhancement mode, while the depletion mode can be used to deplete the channel as it in destroy. So enhancement mode and depletion mode can be summarized in open and normally closed switches. So you have the N channel depletion and N channel. You see that. So this is the behavior of NMOS where when gate is high, that is 1, the NMOS transistor act as a closed switch, and when Vg equal to 0 act as a closed switch. And in PMOS behavior, when gate is low, the PMOS transistor acts as a closed switch, and Vg1 it acts as a open switch. You see, this is the just characteristics I'm telling you, and the parameters. So mostly we have considered two types of parameters. One is electrical parameter and another one is your physical parameter. So in electrical parameter, so threshold voltage, drive current and leakage current. So threshold voltage VTH, drive current is called ion and leakage current is called I off. So leakage current means the value of current at minimum gate voltage. And ion means you see the value of current and maximum supplied voltage. And physical dimension means that length of the gate, depth of the oxide layer, and channel length. So we are talking in terms of these three parameters physically, and in terms of above three parameters, that threshold voltage, drive current, and leakage current in terms of electrical parameters. So this 6 parameters we normally discuss for my design. And now composition of the material, because we are talking about the alternate material, but we cannot think only the alternate material. Whether using that alternate material the design is successful or not, that has to be checked. So here gate material N polysilicon, substrate material indium, gallium arsenide, and it is high electron mobility, 11,200 centimeters square volt per second, where for the silicon it is 1350 centimeters square volt per second. When I am talking the oxide layer material, we are thinking of hafnium oxide, HFO2. The thermal stability, that means melting point, is 2758 degrees centigrade. Boiling point is 5400 degrees centigrade. And it is compatible with substrate material. And here high K is a high dielectric constant. It is a measure of how much charge a material can hold. Here is the reference point for this constant, and K is of 1.0. Silicon oxide, the old-fashioned material, has K of 3.9, such as hafnium oxide, HFO2, zirconium dioxide, and titanium dioxide have a K value higher than 3.9 always. So why we are thinking of this alternate material? Because of this reason, that they have high dielectric constant. You see, normally silicon has around your 3.9 silicon dioxide, but here all of the hafnium oxide, zirconium oxide, or titanium oxide have high K value higher than your K value higher than 3.9. So using this, you see that we have gone for a device structure. So we have done the simulation. We have a visual TCAD, visual TCAD in our lab, in my lab. We have purchased from the DST fund. Here you see single gate, and we are comparing between single gate and double gate, because two of our research scholars are just going to submit their thesis. So I think some of their work I am showing it here, but I cannot supply all the material to you at the moment because they are going to submit their PhD thesis within 2-3 months. So you see one in the single gate, other one is the double gate. So you see single gate MOS and double gate MOS device structure. You see that, you can see the device structure. This is drawn by, you see, visual TCAD 3D. And now characteristics of the MOSFET. You see that we are talking about the single gate and double gate, and we are talking about a threshold voltage, and we are talking about 10 nanometer gate length, 8 nanometer gate length, 6 nanometer gate length, and 5 nanometer gate length. So we are talking about 4 different gate length. So all of this paper has published in ACI journals. So you see the threshold voltage for 10 nanometer, you see single gate, you see 0.40961. But in case of double gate, when we are talking about a double gate, you see it's almost half, 0.2762. In case of 10 nanometer gate length. Again, in case of 8 nanometer gate length, you see that threshold voltage for single gate, it is 0.3579. But for the double gate, it is 0.26. So in 6 nanometer, we have also successfully designed 6 nanometer. It is 0.2360. But in case of double gate, here little bit high. But we can justify in some other ways. When we shall go towards the end, we'll show you. In 5 nanometer also, you see, when we are coming down to below the 6 nanometer, 8 nanometer length, here for the double gate, you see threshold voltage is increasing. Now, let us consider the material. What are the materials we are considering? In case of 5 nanometer, we are considering silicon germanium, indium gallium arsenide, gallium nitride, and the gate length is 5 nanometer. You think of it is sub-regime of your 10 nanometer gate length. So you see the matrix. I have told that electrical parameters, 3 electrical parameter we are talking about: ion, I off, and threshold voltage. So for single gate, you see the threshold voltage is 0.1758. But when I am going for double gate, it is 0.05. So there is an enormous difference of threshold. Now, I off. Here you see single gate 6.1 10 to the power e to the power minus 8. Here it is e to the power minus 9. And ion you see 7.4 10 to the power minus 7, e to the power minus 7. Here you see 2.37 into e to the power 3. So you see for single gate and double gate, when we are using SiG, both case, when we are using indium gallium arsenide, let's consider that. You see, here ion is 44 for single gate, e to the power minus 7, but here for the double gate, you see that 1.26 e to the power minus 3. I off, here you see 0.007696 e to the power minus 8, but for the double gate, 2.8 e to the power 6 e to the power minus 11. And threshold voltage, again you see for single gate 0.38, but double gate 0.57. We have designed all these gates. For gallium nitride, again we are using another alternate material. So for single gate, you see 9.7 e to the power minus 7, but for double gate 4.82 e to the power minus 3. And I of 0.03 e to the power minus 8, but ion double gate it is 1.02 e to the power minus 9. Threshold voltage here you see for the gallium nitride, it is here 0.61 for the single gate, but double gate is 1/3 of that. You see, we are using the alternate material of silicon, but we are getting a very good performance. So for the 10 nanometer sub-resin, we can show you that these characteristics are prevailed. That means the use of alternative materials is very important when you are coming down below the 10 nanometer range. So you see this CMOSFET, combination of both N-type and P-type MOS, this is the structure. And you see this is the structure of design from your Visual TCAD. Now let us consider the performance in terms of the power. You see, we have used 4 gate length, 10 nanometer, 8 nanometer, 6 nanometer. Characteristics all are coming perfectly IDVG curve and IDVG curve for PMOS and NMOS. This is your IDVG curve for NMOS and this is IDVG curve for PMOS. For all CMOS devices, you see, absolutely fine for that. You can see it. Those who are from the electronics field, you can verify it from the nature of the curve. So for the 10 nanometer gate length, the performance of average power 1.36 into e to the power minus 7. For 8 nanometer, you see 9.67 e to the power minus 8. 6 nanometer, you see e to the power minus 7. 5, you come down 1.98 e to the power minus 7. So for analyzing the performance, you see we have used this formula can equal to this W mu n COX by 2L, K equal to conduction parameter, W হচ্ছে channel width, mu n হচ্ছে electron mobility, COX oxide capacitance, L equal to channel width, ID equal to Kn VGS minus VTH, VGS minus VDS equal to VTH. So ID is called the drain current, VGS is the voltage supplied gate to the source, threshold voltage is VTH, and VDS is the voltage supplied drain to source. So these are the metric we have used for analyzing of this. And for the electrical characteristics, we have used this, all of these formulas. N equal to this W mu n COX 12, ID equal to Kn VGS minus VTH, COX equal to epsilon x by TOX, and epsilon x equal to Ei minus electric constant x permeability of the vacuum. So you see the performance here, IDVG curve. So horizontal blue line indicates the supplied voltage. So this line is showing the supplied voltage. And vertically orange line indicates the drain current with respect to the gate to source voltage. And your blue line indicates the device performance at below threshold voltage, and orange line device performance at the greater value than threshold. So you can see the performance is optimal. Now, after that, not only we have used the alternate material to design 8, 6, 5 nanometer. Let us consider that all these three only. Now, whatever possible I could show you that 8 nanometer single gate, 8 nanometer double gate, 6 nanometer single gate, 6 nanometer double gate, 5 nanometer single gate, and 5 nanometer double gate. So first we have designed the inverter circuit. You see, for the inverter circuits, what is average power? You see 9.67 into 10 to the power e to the power minus 8 for the single gate, and for double gate 1.44 e to the power minus 11. For 6 nanometer design, it is 9.89 e to the power minus 7, and for the double gate 0.07 e to the power minus 6. So 5 nanometer single gate 1.98 e to the power minus 7, but for the 5 nanometer double gate 5.39 e to the power minus 6. This is the average power. And you see that this gate we have designed inverter NOT gate circuit, and this is the schematic of the NOT gate circuit. You see the transient output characteristics curve. You see your, you see just opposite to this, your blue is the input and red is the output. You see, so it is perfectly working as an inverter. Then we have design AND gate. Here you see that average power for this gate for 8 nanometer, 6 nanometer, and 5 nanometer. For the single gate 1.28 e to the power minus 9. For double gate 1.04 e to the power minus 13. 6 nanometer single gate 4.09 e to the power minus 6. 6 nanometer double gate 1.63 e to the power minus 6. 5 nanometer single gate 6.74 e to the power minus 6. 5 nanometer double gate 9.83 e to the power minus 6. So you see we have simulated the AND gate circuit, and this is the AND gate transient output characteristics curve. You see your V in 1 and V in 2. These two color are V in 1, V in 2, and this blue color is V output. That means for case of AND gate, when both inputs are high, output is high. You see that clearly shows from this curve. Then we have designed the OR gate. you see, again the average power. This is a schematic diagram of the OR gate circuit. So this is the average power for 8 nanometer single gate, 8.20 e to the power minus 9. For double gate, 9.94 e to the power minus 13. For 6 nanometer single gate, 8.35 e to the power minus 6. And 6 nanometer double gate, 1.75 e to the power minus 6. And 5 nanometer single gate, 1.71 e to the power minus 7. 5 nanometer double gate, 9.88 e to the power minus 6. And you see, based on the characteristics of the OR gate in Boolean equation, you see, it satisfied the curve here. You see, this blue is the output. So in OR gate, output is low when both of the input is low. Otherwise, output is high. Then we have designed the NAND gate circuit. This is the schematic of the NAND gate circuit. And you see that for all, we have given only one curve. For all cases, the curves are there. So you see for the average power. So for the 8 nanometer single gate, 3.99 e to the power minus 9. For 8 nanometer double gate, 2.19 e to the power minus 12. For 6 nanometer single gate, 1.51 e to the power minus 7. For 6 nanometer double gate, 0.14 e to the power minus 6. For 5 nanometer single gate, 1.24 e to the power minus 8. For 5 nanometer double gate, 5.66 e to the power minus 6. This is a NAND gate. So when both inputs are low, the output is high. So you see that output is high when both inputs are low. Then we have implemented the NOR gate using all of these alternate materials other than silicon. And here you see for 8 nanometer, 6 nanometer and 5 nanometer, in case of both single gate and double gate, the average power is 2.68 e to the power minus 7, 5.39 e to the power minus 12, 4.12 e to the power minus 7, 2.58 e to the power minus 6, 5.06 e to the power minus 8, 5.77 e to the power minus 6. And here you see this is a NOR gate. So you see that if here it's satisfying the exact property of the NOR gate in terms of V out here. You see, they all are 0. And then when there's 0, this is high. Then we have also designed the exclusive OR gate. You see, you have used the 4 element of the gate, and you see these are the inputs. You have designed the XOR circuit. This is the schematic of the XOR circuit. And average power you see for 8, 6 and 5 nanometer, see 8.08 e to the power minus 7. For 8 nanometer double gate, 1.97 e to the power minus 13. 6 nanometer single gate, 1.68 e to the power minus 7. For 6 nanometer double gate, 0.81 e to the power minus 6. Again for the 5 nanometer single gate, 1.03 e to the power minus 7. And 5 nanometer double gate, 5.45 e to the power minus 6. And it is the exclusive OR gate. So when either input is 0, when 0, 1, 1, 0, output is high. So that's why you see it is clearly showing by the blue curve that 1, 0, 0, 1 is high. 0, 1 is high. So someone may say there is a gap between these two. So there is within the permissible limit of the ITRA. That it is not exactly 1. So some 0.9 or something is coming, but it is within the permissible limit of the ITRA prescription. Then we have also designed the XNOR gate, circuit schematic of the XNOR gate. So you see there, average power is for the 8, 6 and 5 nanometer. You see that there is a single gate 3.37 e to the power minus 7. For double gate 3.24 e to the power minus 13. For single nanometer 6 nanometer single gate 4.28 e to the power minus 7. For 6 nanometer double gate 0.66 e to the power minus 6. 5 nanometer single gate 8.898 e to the power minus 8, 5 nanometer double gate 5.56 e to the power minus 6. You see, and this is the curve for the XNOR gate. So when both inputs are identical, outputs are high. You see, both inputs are identical. Here, you see outputs are high. So now, future. What is the future of the transistor? See, according to the IEEE IRDS, International Roadmap for Device and Systems 2023 nanometer logic CMOS technology will start production. So, the real minimum line width length is 15 nanometer for the 3 nanometer technology in IRDS 2021, and downsizing limit of the minimum line width such as the gate length and material wear width is thought to be about 10 nanometer because of the significant increase of leakage current of MOSFET and resistance increase and reliability degradation of interconnects. So the scheme of device miniaturization having continued since the invention of the transistor. So there will be no pico technology. I have already discussed after nanotechnology. So progress of integrated circuit to Moore law will continue by 3D integration. But cost of 3D integration is surely will be high. So AI technology will be used for that. And till then, 10 to 20 years, so 3D technology, 3D integration will be there. And future intelligent society will create another directions for this technology. So some of the publications I am showing it here. You see, is some publications in microsystem technology, some publications in physical scripta of impact factor 2.6. So these are some of the recent publications based on this study. These are of the publications on based on which I have prepared the slide. So my conclusion is that indium gallium arsenide is found most suitable candidate as an alternative of silicon. During my this tenure of lecture, so only one conclusion for my study in my lab, I can say that indium gallium arsenide is found most suitable candidate as an alternative of silicon as a semiconductor material, and hafnium oxide has been found as an alternative silicon dioxide as an insulator. This is my conclusion of this lecture. So these are some of the references. So someone may ask some questions. I love to interact with you. Thank you very much for patience hearing. So next 10 minutes. So I shall go for question answer. So I think over to organizer. If any questions are there, so we shall discuss next 10 minutes. Any doubts or anything?
Okay. Am I audible?
Yeah, absolutely.
Okay. Thank you, sir. Firstly, we extend our heartfelt gratitude to Professor J.K.M. sir for accepting our invitation and delivering an insightful lecture on the topic that is the role of alternative of silicon for the design of semiconductor devices and IC. In today's world, we are living in the era of semiconductor with the silicon is the backbone. And Professor J.K.M. sir actually demonstrate excellently step by step evolution of this semiconductor technology from its early days and to the present day where we are actually. And he highlighted the semiconductors are no longer limited in computer but to extend to our daily life as an entertainment from normal computer to form supercomputer, IoT, and AI with the upgradation of technology, ICs, and the chip circuit. However, the challenge is the Moore's law that we are reaching in 2025 the size limitation and physical the limit of these devices. So we need a alternative. So that's why, and sir has explained all the research, current research. He and his students are actually working on that to solve these issues. And sir has also mentioned that the alternative is bio devices or biochip, which are the next future in this IC industry or semiconductor industry. And we need to overcome this semiconductor with a modern AI based or circuit design or by alternating material like carbon or graphene or any other alternating 2D material for get more performance or size compression with this technology. So now the forum or platform is open to all. And another time, thank you, sir, for explain all the things so beautifully to all of us. And now, if from audience or participant have any query, any interaction, you can, yeah. Mitali Shen, many people raise their hand, so you can unmute and ask your question.
Yeah, no problem.
May I ask you, sir, a question?
Please.
Sir, myself, Dr. Binay Krishna Vishwas from Vivoda Institute of Technology.
Yeah.
It is very informative. Sir, though I am from not this field, I'm just you have already explained, but further I want to ask you, so what's the limitation of this silicon so that we have to think the alternative of the silicon apart from the silicon?
Because you see that the first thing is that your K, value of the K, the first thing, and second one is the temperature, and you see the ion and ion current ratio. That is main cause for that. When you are slicing down the size, we are facing the challenge at that moment. I have shown you clearly. Always it is, I am talking about the sub-regime of 10 nanometer. Always we are talking about the sub-regime. I am not talking about the higher range. Even you see, Government of India has given a lot of funds for this research. Even they are challenged that because we are still in 160, 180 nanometer fabrication range in Chandigarh and Bangalore. So next 5 years, lot of funds are giving for this industry, and industries are coming up. Even at Kolkata also some MOU has been signed. So next 5 years, coming now to the 20 nanometer in India, we are talking about the designing of less than 10 nanometer, 10 nanometer. So challenge is there only for the silicon.
Sir, one more question may I ask you?
Yeah, please.
So, sir, less size means less than 20 nanometer, that is designing in India. Is there any scope to manufacture in India in that types of things?
No, it is not there still now. That is a problem. That is a problem. We have some industries are developed at Bangalore. They are doing, lot of funds are flowing from the Government of India. They are trying to fabricate. Lot of small fabricators of lower gate lengths are going on. I think within 3 to 5 years, you will get lot of things at India. And as a result, cost will also be reduced.
Thank you, sir. Thank you, sir.
Any more questions? So, sir, I have one question, sir. So, actually, nowadays we are very much learn or very much talk about the quantum computation, and another group of or school of thought, they are talking about the neuromorphic computation. And can you briefly explain that the difference or what are the, briefly, can you just say something that what is the neuromorphic computation and what is the quantum computation from these normal von Neumann computations?
Actually, these are entirely different paradigm. You cannot compare with these two. When I am talking about a quantum computing, it is not in the normal temperature range. we are talking about still in the normal temperature range in that subdomain of 10 nanometer. There we are not that in that. There you see that it is a cryogenic state. So that you have to maintain in some way. And then you can go for whatever the qubit and 2-bit, 4-bit, whatever the available as a computers and IBMs and others. So those are in that way. Only you can simulate that from your, you are not exactly getting on that. So that is the basic difference what I can say at that moment.
And what about the neuromorphic computation, sir?
Neuromorphic computations, I don't know much about that because I'm not working on that line. So still you see that neuromorphic computing, we see that physically how do fabricate that neuromorphic computations. Information processing is okay, no problem, just like your bioinformatics. But when I'm talking about the neuromorphic computation, so in that case you see that if we go for in quantum computation, we are talking about the spin in terms of the magnetic field. So if spin orientation is x direction, so we are talking about a 0, and a spin is the other direction, we are talking about that. But in neuromorphic computing, you see that's a neuron to be simulated in terms of the flowing of the network in terms of the zeros and one. That will be simulated in that way. That's up to, I know whatever we go. I didn't work much on that.
Okay. Thank you so much, sir, for enlightening on this.
So,
Any query?
Biswajit Kundu sir, we have any query?
Yes. So a substitution for silicon. Currently, to make the gallium arsenide based device, we need to follow some epitaxially grown method, which is very cost effective. So in this perspective, how we can overcome this cost effective process to
Your voice is breaking. Can you repeat? Your voice is breaking. Actually, cost effectiveness is there because you see that whatever we are doing, we are doing in the lab. So fabrication part still is awaiting. So that part, the validation part, we are validating in terms of the IITA reference only. So we are not going for any validation still now. So next step we shall go for it. But fabrication process is not in India, that we have to go abroad for that.
Yeah, because in case of indium gallium arsenide, currently the epitaxial gold method are followed. So that's the reason.
Yeah. Normally these methods are followed. So, but that fabrication possibilities is not here. That is one major problem.
Okay. Thank you, sir. Thank you.
Thank you.
Hello, sir.
Yeah.
Yeah, I'm from Bangalore, basically.
Yeah.
You told some semiconducting they are doing in Bangalore. May I know which is that company?
I cannot say exactly. So later on, you see, you can provide my mail to them so they can interact. I will give them the references. It is not with me. It is there. They are doing a lot of work. And some industries are coming up at Bangalore. So you can contact with them. You can do work. Oh, they are happy to be associated with you. Okay.
Can I ask one question, sir?
Please.
Myself, Somu Mukherjee from Kazi Nazrul University. I am from metallurgical background. I just want to know, when you are proposing these materials, are these necessarily single crystal based or polycrystalline based for semiconductor application?
No, these are mostly, actually, we are not going for mostly single crystal. But here you see that it depends on your simulator. Mostly what materials they are providing. These TCAD, 3D TCAD we have purchased, I think 8 years back with the cost of 7 lakh for 4 terminal we have. But now you see that graphene, we have tried for graphene. So they are telling that you have to pay another 13 lakh. So that is very difficult. As a state-aided university, this is very difficult to go for it. So that's why you see that material alternatives are, we have tried for graphene also, but we could not do because they are not supporting. Even you see that I did not give it here. So we have gone for some security circuit. Some symmetric security algorithm we have implemented in hardware. But you see, up to 2-bit we have implemented. we cannot go for more than the number of transistor. If you accumulate at a time, suppose it is more than 18, it cannot simulate. It takes 5 hours to 10 hours. So that we cannot go for it. So, but for that we have to go for the new package again. And that is a very costly. That's why I could not experiment that polycrystal or single crystal like that. It is not beyond our scope of my whatever I have purchased 8 years back.
Okay, thank you, sir.
Sir, I have a simple question.
Yeah.
So actually, we have in India a lot of software company, renowned
Yeah.
software company, and we are not making any ChatGPT like platform till
Hmm.
now. So all are coming
Okay.
from recently NVIDIA based on USA and DeepSeek from China. DeepSeek crashes
Yeah.
the NVIDIA because
Hmm.
DeepSeek are more faster than NVIDIA like AI ChatGPT. So what is the reason behind this? First of all, why we are not making this type of chat platform till now, as we have a lot of potential in India. And in case, okay.
No, okay. You just complete it. No problem.
And in case of you just talking about semiconductor, there is a lack of fab labs. It costs high more. Okay, I understood everything. But if in terms of software, AI-based software or chat GPT like platform, why are not able to create it till now?
I think this is a funny question because you see, if you see that people from India are going abroad and they are taking part of this design. This is the first unfortunate thing. And second thing is that again I am also that giving you the same question to you, that you see still now all GIS based software we are purchasing from abroad. Not a single GIS based software is written at India. But we are so strengthful in your remote sensing and GIS application, particularly from the angle of ISRO. Because of the reason is that, so when you are getting a chance for better opportunity, you are going to abroad and there you are designing. You know that this CMT, whatever we are using in various conferences and other, this is designed from a technologist. He resided originated from Kolkata, but he has designed at USA only. So these things always going to happen. That means, how do we keep the upcoming talent at our country? That means the investors should do that. So investors should come out. So particularly that's why the emphasis from the government of India is that, so they are investing a lot for the electronic industries in various places, so that it again come up and they can join for development of our country and the resources at our country, within the country. That's initiation has already been started, but I don't know when it will come up.
Okay, thank you, sir. So one more question, apart from your selected title, I have heard lot of lecture from you. So as you know, ISO convener of world. So educational institute, how to get the ISO mark? ISO, there are different types of
ISO
ISO.
certification.
Yes, for educational institute, what is the criteria?
I don't know. Actually, I am leading one work group from the world. It is access for all. That means when you are writing some ebooks, or when you are writing some material for a class 6, class 7, class 8 or class 12 students, how it can be written in such a way that everyone can access. And then that means even the disabled means disabled in terms of the computation, not in terms of the physical disability. That is when you need that A plus B equal to C, how picture can show you that A plus B equal to C, so that I can understand in a better way. That is, my disability will be removed completely, that I can understand in a better way. So I am heading that, and two standardization is going on. So I am a lot of busy with that work. But regarding the ISO certifications, you have to go to the ISO portal, and there everything is given. You can go to the ISO portal. All norms are written there very lucidly. You can see. I am using ISO portal, but I am using in my part as a convener and as a organizer of ISO or official of ISO. So I am not aware of that. So you can contact with me. I can take data from others, those who are head of the ISO. So I'm so even yesterday there was a meeting. So I can tell you later on after getting.
Okay, sir. Okay, thank you, sir. One more, another silly questions. I mean, I have a lot of curiosity. So when you making voice call today, there is a data free call. Okay, voice call is free, but that has been can be recorded. But when WhatsApp calling cannot be recorded. What is the reason behind this? WhatsApp
Because
can
WhatsApp,
someone make a WhatsApp call, it cannot be recorded.
actually, you normally see that I'm telling you, because of the reason that when you are calling WhatsApp, your voice is there. Then from that voice, it is called, it is written there. You will see that end-to-end encryption. What is end-to-end encryption? That is a different from normal encryption. They used to negotiate between two devices. Suppose I am calling you through WhatsApp across the globe. So you and me, your device and my device. My device may be Apple, your device may be Samsung. So two device, my device may be of 80,000, your device may be of 10,000. Both are smart mobile. So my device support 1000 encryption techniques, your device support 100 encryption techniques. So on the real-time negotiation basis, they used to choose a protocol. And using that protocol, they used to encrypt it. And it used to send the voice to the encrypted data. So if you try to record as a screen recorder, it will be encrypted voice. You will not get it. And that's why it is not, that is my perception. And then it will, when it is going that, it used to take the same protocol, it used to decrypt and coming as a decoded voice. But when the session is completed, the negotiation goes up. Suppose after 1 second, I am talking with the same person. So another negotiation will go and another protocol will be initiated. And that is quite random. That's why it is very difficult to record. You have to break the encryption. That is not possible because they are not using any standard encryption process. They are negotiating between two communication devices and that used to go for that encryption. That's why it is called the end-to-end encryption. And that is the process.
Thank you, sir. Thank you.
Thank you. And so one more question from my side, that so as you mentioned that biological or bio, because as the title of this program is the sustainable development. So whenever we are going to fabricate this silicon-based device or the IC or the fab lab consume lots of chemical, lots of hazardous chemical and the waste. So from the point of view of sustainability, so what is the future for that, or how we can replace it, or what direction we need to focus on that? One direction you said that replace the silicon or try to modify with other material, but when we are going to fab lab, again the lots of chemicals and lots of waste are coming out. So what will be the goal should be there for this?
So you see that UNESCO has defined the 17 sustainable goals. So out of these 17, one of the goal is this. That's to tackle with the chemical industry and electrochemical industry particularly. So they have a lot of operative procedure there. That how you go for this disposing of this material. When you have a printed circuit board, you see you have lead as well as you have all other things. Even printed chemicals also there. So they have given some separate prescription for that. You have to follow that. But unfortunately, we are not following that. We are normally dumping that in a ground. Most of the cases, that is not the sustainable goal, achieving of that goal.
So what direction we need to think, or what
The
will be
direction that when we are disposing of all this material, or when we are going for the disposing of the waste or the rest of the materials, remaining materials after your fabrication and all other things, that has to be disposed in terms of that SOP of that sustainable goals, that chemical waste, whatever the goal has been prescribed, that then only it can be reduced.
Okay. And one thing, that is a biocompatible chip. So it is, will we have any future biocompatible chip, or?
And that is gradually coming up. I don't know where. I think there is a promising directions they are taking, biochip. Because you see, it started from the Jagadish Bose, that plant has life. He has proved it with the instrument even.
Yeah.
So still now it is not there. You see, the Hofmann tree was invented by Hofmann in 1949. Then it was a static, two-phase static Hofmann tree. First pass is used to go generate the probability distribution. Second pass is you are going for the compression. After 36 years is 1985. From 1949, Knuth has developed the dynamic Hofmann. You see that years it used to go for a dynamic modulation of that particular technique for communication. So that will come and it will take a place. That is, I think, my perception is like that.
Okay. And thank you so much for this wonderful session and wonderful lecture you have give to us and enlighten us in all different directions.
Yeah, this is my off. I think what is known me. I am known for the security peoples, and mostly I am working there. But I think it's a very less people knows that I am working on this VLSI for a long time. It's a parallel
really
work. One group of my fellows and all the students and the scholars are working on that. I think two of the scholars are going to submit their thesis on this, particularly single gate and double gate with alternate materials, what we have studied it. Okay, thank you very much for giving me the opportunity to interact with all of you. Thank you.
Thank you, sir.
Okay.
Thank you for your wonderful lecture, and we have learned a lot of things, and we have also cleared our doubt. So now this is our digital platform. So we have a digital memento from Dr. Subarna Institute of Technology and Sports Complex. Now I would like to call upon Dr. Biswajit Das sir. Please share the screen for a token of appreciation as a digital memento from our college. So kindly sir, accept this.
I am honored to accept this token of love from you, and love to be with you anytime when you are calling me to disseminate my thought and my research, whatever I am doing. Because state-aided institutions, we have a very hardship of getting funds. So if I get funds, I can do much more. But we used to do with a lot of constraint. Still, we are working and doing, and we are just competing with, I think, good and topmost institutions. I think that is our, I think, great pleasure. Thank you very much.
Thank you so much, sir.
Thank you.
Thank
you. So, may I delink? Bye.
And good night.
Good night.
Bye.
We will ask you. So our next speaker, Dr. Subarna Shyamroy sir already joined. So I just
so now I like to request our HOD sir, Dr. Dipankar Das sir, to formally invite our speaker, Dr. Subarna Shyamroy sir. He is General Manager, R&T, Head of the Emulsion, Asian Paints. So Dr. Dipankar sir?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. So good evening, sir. Sir,
Sir, you are
please mute yourself.
Am I audible?
Yes, sir. Unmute yourself.
No.
Yeah. Am I audible now?
Yeah.
Yes, yes,
Yeah.
sir. Yes.
Very good evening to
So,
all of you, and I also apologize for about 15
no,
minutes
sir.
of delay because I could not leave office in time today because of another meeting, and I could leave only around 7. So I got delayed in the traffic. Yeah.
No issue, sir. No issue. And thank you so much for your busy schedule. You have accepted our invitation and give time to deliver the lecture. So now this is a formal procedure to invite you. So I request Dr. Dipankar Das sir to introduce Dr. Subarna sir to all of the participants.
Okay, sir. Thank you, sir. So,
Please.
Shyamroy is currently serving as the General Manager, Research and Technology R&D at Asian Paints, where he leads advanced research, polymers and nanotechnology applications. With over 14 years of experience in research, development and industrial leadership, he has made significant contribution to material science, surface chemistry, and polymer engineering. Dr. Shyamroy holds a PhD in polymer chemistry from the National Chemical Laboratory, NCL, Pune, and has completed postdoctoral research at Tulane University, New Orleans, and the University of Massachusetts, Amherst, USA. He completed his BSc and MSc in chemistry from Jadavpur University, Kolkata. He began his career as research scientist at JE India Technology Center, Bangalore, working on materials research and polymer development. He later joined Reliance Industry Limited, where he spent over 9 years in key leadership roles, including General Manager, Specialty, Polymer R&D, and General Manager, Planning, Operation, and Intellectual Property. During his tenure at Reliance, he played a pivotal role in large-scale R&D initiatives, managing industrial projects, and driving innovations in polymer science. In 2016, he transitions to Asian Paints as Chief Manager and Head, Advanced Capability and Nanotechnology, where he was responsible for developing next-generation materials, enhancing product formulations, and integrating nanotechnology into coatings. His expertise in materials innovations and industrial applications has played a crucial role in advancing coating technology and specialty materials research. Dr. Shyamroy has authored several research publications in reputed international journals and holds multiple patents for his innovative work in polymer science, coatings, and nanotechnology. His contributions to intellectual property management and technology development have established him as a key innovator in the field. Beyond his industrial achievements, he remains actively engaged in the scientific community, contributing to knowledge disseminations, research advancement, and sustainable materials development. His career reflects a strong commitment to scientific excellence, industrial innovations, and the future of material science. So thank you. This is the short biodata of Dr. Subarna Shyamroy. So I would like to request Dr. Subarna Shyamroy, please start the sessions. Over to you, sir.
Yeah, thank you very much, Dr. Das, for a very kind and elaborate introduction. Probably I would not myself had given such a good introduction to myself the way you have given. Very kind of you. Now I would, without wasting any time, I will try to upload my presentation on the screen. Just give me a moment. Is my presentation visible on the screen?
Not yet, sir.
No, sir.
Just a second. It is showing some error occurred. Please try again. Let me try. Some problem occurring when I'm trying to share my screen.
Okay. I'd like to, Dr. Dipankar Das, sir, can you make sir as a co-host? So,
I made it. Already made it. Sir,
Oh.
sir is now co-host.
Let me see what I can do. Just a second. I am unable to.
Sir, if you don't mind, can you share this PPT so that we can also share from our end?
Yeah,
To
that is the last resort. I can definitely do that. The only difficulty is that it will.
Okay, sir.
Yeah,
yeah.
I'll have to take certain permissions from IT online. That will take a couple of more minutes. I'll try that, of course. But let me try and understand what is, because it is also not that easy to share. Is any other person's screen already shared by any chance? I don't know what.
No,
In the
sir.
meantime, I'm trying to share this presentation to you. So should I share it in reply mode to the same email address from where I received all the invites?
Yeah. Yeah.
Sorry?
Yes, sir.
Okay, let me try. Sorry for wasting all of your time. I didn't know that this kind of problem would happen. So as there will be nobody of IT at this moment, I'm taking a little bit roundabout way. I'm sending it to one of my junior, asking him to send it my personal email so that I can approve when he sends it. Yeah, just give me a moment to call him.
Yeah, sure. Yeah, sure. You can take your time.
हाँ गिरीश थोड़ा ये टाइम पे अचानक फोन करना पड़ा. I was trying to give a presentation to an academic institute. It's just public domain information based presentation, but somehow there is a problem because they have Google Meet and there is a problem in file sharing happening. So I have just forwarded that to you and just open the mail. You will see that I have given my Gmail address over there. Can you kindly forward that so that I can approve that email? Yeah. Yeah, yeah. Just forward, that will work. So I hope I will receive in a minute. Actually, Google Meet is not in the list of our approved meeting softwares.
Domain.
Only Teams and Zoom.
Zoom. Okay.
So although the software is working, but I don't know, maybe some features of the software is not working. Maybe a limited version is working. So in the meanwhile, I can see there are 120 people, who are also, waiting here. So are they mostly students?
No,
No,
all are
sir.
faculty.
All are
All are
Oh, all
faculty
faculties.
from, yeah.
Various
Because this is a faculty
institutes.
develop, yeah, various institute of
I'm
our
so sorry
country.
that so much of manpower is going. We regularly conduct meeting on Zoom. Generally, no
Okay.
problem of this kind occurs. The approval process got finished. I'm hoping to receive on my Gmail now. Then I can forward to you. Yes, if you don't mind, can you quickly tell me the email address so that I can just shoot it?
Oh, okay. This is HOD underscore BSH.
Small or capital, please?
Small.
HOD.
So can I
Okay.
text?
Yeah, I received it. Yeah, I got it. It is HOD underscore BSH at the rate dsec.ac.in.
Yeah.
Okay. Yeah. Just let me know when you receive it. It's showing sent from my side.
Yeah. Downloading.
Okay. Did you receive it?
Yeah.
So when it downloads, you may kindly
Yeah. It
share
is.
on the screen in the presentation mode.
Yes.
Yeah.
Just few seconds to open it.
Yeah. Actually, when I had received your first request, today's whole day meeting was not scheduled at that time.
Wow.
Otherwise, I would not have ever, backed out once committed.
Okay, okay, sir. No issue.
It's not a very big file, right?
Yeah. Revision presentation more than just 2 3. Yeah.
So,
It is ready, and now I am presenting.
yeah, thank you.
So when you just say, I will present.
Yeah,
It is visible to all participants.
Yes, yes,
is
it
it
is.
visible to all?
Yes, yes.
Okay, thank you. Yeah, now you can go to the next slide, please. So basically, I was requested to talk about, what kind of approaches we take, to make coatings greener and sustainable. So while I have not actually included lots and lots of examples and different raw materials, etc., which are continuously being explored, from various greener and renewable resources. But what I have tried to do here in short, in brief, is kind of capture the approaches, how we think, or what is the kind of strategy we take to make a greener and sustainable future in the coating industry or through the coating industry for the customers. So basically, a greener future, as it is understood, is very closely tied to the idea of sustainability. Now, sustainability, of course, is a very, widely used terms nowadays, and it can have various meanings. A, it could be energetically sustainable. B, it could be sustainable from the supply of material point of view, supply of raw material point of view, or it could be sustainable from the life cycle point of view as well. And it could also be sustainable from the point of view that it generates less non-degradable wastes, etc. So I think we all are trying across various industries to adopt as many of these approaches as possible. Not everything is possible always at the same time, but sometimes we may try to reduce the energy consumption. Sometimes we may try to use a lesser carbon footprint, fossil fuel footprint. Sometimes we may try to see that the material actually lasts a lot longer, thereby the waste is reduced, because every time a material expires its life after end use by a customer, it invariably go into the waste. So if a material lasts longer, it is a double benefit. Sometimes it's a benefit for the customer as well, in terms of longer warranties and longer shelf lives, and maybe when we talk about coatings, longer uh, life on the walls and the different substrates on which the coatings are applied, so that the customer does not have to spend time and again, every year or every 2 year or every 3 year to do the same kind of painting, coating, etc. Even that is also a means of sustainability. Typically it is more beneficial to the customer, and because it is more advantageous and beneficial to the customer, typically our kind of industry, like the coating industry, tries to give longer warranties. Okay. Now, one might think that while it is beneficial to the customer, it might be loss making for a company, because if warranties are shorter, then the same material can be sold many times over in frequently. But the thing is that when customer gets a longer warranty and a longer life on whichever substrates he applies a coating, the customer is also ready to pay a premium for that. So therefore, then the company which is delivering that coating or paint also earns a higher premium, and then at the same time, the volume sales also increases. Okay, so that's why the company also starts benefiting. So then it becomes mutually gainful, for both. And so this is an example that I gave about a kind of means to increase sustainability in the business, which is longer life. Now, similarly, better performance is also a kind of sustainability, because better performance generally also provides longer life. Sometimes the reason is that let's say complaints, etc., would reduce, and higher degree of an advantage will be accomplished by a customer, and hence he would not have to try an experiment with different paints and coatings frequently, okay, to get the same advantage or same performance. For example, if somebody wants a paint on the wall which will not be attacked by the sunshine or the algal or the fungal, etc., kind of attack, that means that it's giving a higher performance. Now, apart from the longer life, the customer would be would remain attached to a paint of that kind, and he or she would not try an experiment with different paints of different companies, and hence would not generate more and more waste. It is a little different from longer life, because if the performance is not liked, then even though the paint on the wall has life left, the customer may scrape it and go for another coat of fresh paint or a repaint. Okay, so that is also a means of attaining sustainability in the long run. So why I a little bit took time to talk about these two aspects of sustainability, particularly from the coatings point of view, because these days, sustainability is almost equated to green. Okay, I just wanted to say that sustainability is always not equated to green. Even if your coating or any other product, for that matter, is not necessarily from a greener source or a biologically derived source, it doesn't mean that it is not sustainable. And I would also like to say here is that sometimes if your raw materials are biologically derived or biologically sourced, we may take pride that we are using renewable raw materials, etc. But we have to also keep in mind that we are also depleting the renewable resources And although we call them renewable, they are not really so fast renewable. And therefore, for example, in our country itself, there is another government agency which is looking at this aspect, which is called National Biodiversity Authority. Okay, and they have framed very strict and very beneficial rule, which is not only looking at our generation, but for looking at successive, descendant generation of ours. They have said that if you are using a biologically derived material, okay, then you have to declare. Okay, and then biologically derived materials are actually the country's wealth. Okay, and hence in certain circumstances, especially if you are not 100% Indian company, you may even have to give a royalty to the government for using our country's biological resource. Now there are several exceptions to that, when you have to pay the royalty, when you don't have to pay, and all that. So, but without going into those nitty-gritties, what we can understand is that even preserving our so-called renewable resources and biologically derived resources also equally important, as it is important to look at the global warming and the carbon footprint and stuff like that. Okay, so that is another aspect that I just wanted to say when we talk about sustainability. So sustainability is not equal to green. That's the first thing. Sustainability is anything which is any material or any strategy or any means of delivering and servicing a product which is good for the humankind for a long duration of time. That is more or less is actually sustainability. There are various other rules and regulations related to use of biologically derived materials also. So for example, there has to be complete non-compete with any edible material. Edible doesn't only mean edible to humans, it also means edible to the whole animal kingdom, etc., etc. Lots of things are there. So therefore, when coating industry looks at sustainability, it looks at it from the approaches that I initially set out to set. So then, in that manner, which means that it has to be good for humankind, okay, and good for the whole environment, all the other species of environment. Just in that regard, I may also say that while in our coating industry, while we do not want our coatings to be attacked by bacteria, algal, and fungus. Okay, now the thing is that the approaches so far, of course, has been to kill them, okay, by using chemicals in the coatings, either when the paint is in the can or it is on the wall. But gradually we are trying to move to a direction where, we don't kill, instead of biocidal, we are talking about maybe bioremedial or resistant to microorganisms of various kinds instead of killing them. Then while maybe you have a paint, you want to protect it from algal and fungus attack, and hence you are adding certain chemicals to it. But there are existing regulations which tell us that your chemicals cannot leach out to that extent where the grass beneath your building is burnt, for example. Okay, or you may be using certain surfactants and certain fluorinated compounds, etc. There are regulations which also bind us to ensure that.
Are you changing slide?
No, I have not. I'm just speaking on the 3 points that I have written here. I'm elaborating. Okay, so you cannot destroy the aquatic life also. So this is another way that sustainability is being taken care by the coating industry. I'll go into a few examples after this slide. So the first thing that the coating industry started historically, to look at sustainability, and it was started long back, was that how we can reduce the release of volatile organic compounds into the atmosphere. Okay. Now that is the first example. Now, so far I was talking about little bit theoretically as to what are the ways and means. Now, this is the first example of specifics. So the first aspect of sustainability is lowering the volatile organic compounds, or VOC, into the release into the atmosphere. Let's say if I am making a paint, as on today, as I speak, in the Indian context, the maximum volatile content releasable from a paint is set to 3000 ppm. Okay. Now, then there are certain other regulations which are not Indian, which are global, but some of the forward-moving and progressive paint companies are voluntarily trying to comply with them. For example, Green Seal, TS11, etc., wherein the total volatiles will have to be kept below 1000 ppm instead of 3000, and individual volatile raw materials release may have to be kept in certain cases below 100 ppm. Like if you have 10 volatiles, your total may be 1000, but individual should be less than 100. So these are some of the regulations which are not binding in India, but still the progressive paint companies are trying to comply voluntarily with them, so that, of course, there is a little bit of commercial interest as well, because when paint companies voluntarily comply with such global, norms, then, that also earns the respect of investors, not only the Indian customers, and investors are global. So therefore, as you see, that it is also important to have the respect of your coating brand globally, and not only in India, although your operation on and sell may be in India. So VOC is the very, very critical and important parameter of sustainability. Then, as I was saying, companies may also now consider the broader impact of their activities to the society and the concept of eco-efficiency, eco-friendliness, etc., etc. So eco-efficiency is the ability to satisfy customer needs in a way that minimizes adverse effect on the environment, natural resources, human health and safety. For example, EHS, the environment, health and safety, that even in the Indian context also, with any of the progressive paint companies, is a very strictly adhered to aspect, the environment, health and safety. I'll just give an example. For example, in our company, we have a long list of raw materials and chemicals, which we call as highly hazardous raw material, HHRM. Okay. And then we have categorized them in 3 bands, 4 bands actually. Red, orange, yellow, and green. Green is ultimately non-hazardous, and then red, orange, and yellow are the 3 categories of hazard that we say. Now, red means you cannot even touch those raw materials, however attractive they are, for the purpose of producing certain kinds of paints and providing certain kind of performance. Orange and yellow are 2 categories where you may use them in certain circumstances, but you have to take enough precautions, restrict their release values to a certain extent, and also you have to take enough care of the employees, at the shop floor, at the logistics, at the supply chain, at the marketing and sales, whoever is handling, either those chemicals or the products out of them. Okay, so that kind of strict compliance is also maintained in terms of environment, health and safety in any of the progressive paint companies. So, and that I just wanted to emphasize that even that also is a part of sustainability, and not only green. Green actually comes at the end. Okay, yeah. Now you can please change the slide. So, okay, this slide we may keep because I think I have already spoken on this importance of reducing environmental damage to the coatings due to the coatings. Yeah. So you can skip this slide and move on, please. So what does a green future in coatings look like? The 3 key elements of the modern idea of sustainability are, like I said, circularity, which means that I should be able to recycle and reuse some of the materials at least. Then preventing climate change, which may happen in various manners. On one hand, I should try to reduce the carbon footprint, but at the same time, I can't indiscriminately use biologically derived materials just in the name of reducing carbon footprints or green. Okay, like I was saying initially, and then ensuring the health and safety, the EHS. So basically, the three criteria are recycle, reuse, criteria number one. Criteria number two is look at the climate change in a holistic manner, and then comply very strictly to the EHS norms and regulations. And when we talk about EHS norms and regulations, it has to be both your customers as well as the workers, not only the customers alone. Next slide, please. So reducing VOC, I think I have talked enough on this, on the importance of this. Just to give you a little bit of specific examples, I can say that one is, of course, I talked about how minimum you can keep the VOCs of volatile materials. Another important approach to use some non-volatile materials in place of volatile materials by technological advancement. A very specific example I'll give you is that there is a very common thing in coating and paint that is used called coalescing agents, which means that the emulsion particles of the paint should coalesce into each other to form a good film. Okay, because forming a good film is important for the property, performance, life, as well as optical beauty of a paint. Now therefore, coalescent is one very key raw material which is oftentimes needed, and not in very less quantity, but in quantities anywhere between 2 to 3%. Okay. Now the thing is that you may not be able to get rid of coalescent, and they will add to certain VOC, because the coalescent working mechanism is such that when your paint is wet, they will have to work to give you a film. But once the film has formed, they will have to go out of the paint by volatilization in the atmosphere. Unless and until they go out, your paint will not dry and harden. So therefore, as long as you have a volatile coalescent material, it must generate VOC. Okay, and you can't reduce it below a certain limit. Then the research is going on in the direction that how can we create non-volatile materials which give you the coalescence action, when some solvent or when some solvent or water is present in the film. But when the film is drying, even the coalescent material should also dry. So somebody asked, put a question in the chat, give some example of such coalescent materials. They are basically some esters. You can say they are actually esters of polycarboxylic acids. Typically, coalescents are like that, and they are volatile, but very slowly volatile. Their volatility constant is not very high, like solvents, because of their little larger molecular weight. But eventually, they are volatile. They may take anything between 15 days to a couple of months to actually go out, so fully. Now people are trying to create polymers, low molecular weight polymers, for example, which will give sufficient plasticization or coalescence action when the along with the solvent or the water, when they are present in the system. But as they are a little bit polymeric, because of that primarily, and also because of certain types of reactions in presence of air or moisture or sunlight or something, that people are trying to build on the backbone of such macromolecules or low molecular weight polymers, so that along with the main paint drying duration, this thing also dries. Some people are trying to make them in such a manner that they slowly, very slowly react with the polymers main polymer of the paint, or some people are trying to make in such a way that they very slowly react with the pigments and fillers and extenders, some of the pigments or some of the fillers or some of the extenders present in the paint. So basically, for example, if you want to make non-volatile coalescing agents, you have to make it little higher molecular weight than just molecules. They have to be towards polymers, but at the same time, which are very soft, very plasticizing, and at the same time, which are reactive in some or other manner. So that's the kind of technology advancement that people are trying to do in the industry, so that they can minimize the VOC coming from the coalescent. Okay, now VOC coming from monomers, the basic monomers like styrene, acrylates, etc., or some of the glycols of the alkydes or polyesters. These are the basic monomers which are required for the basic polymeric binders of paints. Now, whichever volatile components they have residually after the polymer has formed, they can't be made zero, but they can be minimized below 100 ppm. But the coalescents can actually be made zero. I mean, there are no other option. Either you have a couple of thousand ppms anytime of the VOC coming from coalescents, or you get it to zero. There is nothing in between, almost. Okay, so that's how it is. This is just one example how to deal with VOCs. Now, of course, to deal with VOCs coming from the different monomers, there, definitely and obviously, we are focusing on how to increase the polymer yield. Okay, what remains as VOC is nothing but the unreacted monomers. So we have to ensure that very, very close to 100% of the conversion of monomers to polymers have happened. Okay, so that's the only thing that we're trying to do. So there are, everybody is trying to do his bit in his own way to maximize the conversion. Next, please. Increase in bio-based ingredients. So I again talked about it. Now, as I said, that they are not the only way, but they will come towards the end of the list, but yes, they will still come because, after taking all due care, about the strategies and norms and policies that organizations like the National Biodiversity Act tries to implement in every country, all those care has to be taken so that the biologically derived materials are also not indiscriminately used and depleted of the earth. So now we are depleting the minerals and fuels of the earth, and if we are indiscriminate as humans, we can deplete the biologically derived materials also. We can deplete the forest, we can deplete maybe certain organisms, and we can deplete many such living things. And while depleting the non-living things, we kind of can calculate what is going to be the fallout and how long it will take. But then while depleting some of the living beings, whether from the plants kingdom or from the animal kingdom, sometimes we don't even know what is going to be the impact, because their impact are very, very interdependent, right? Depletion of one particular or extinction of one particular organism can take a toll on a whole environment of a particular segment of the world. Okay, so those risks are actually much higher. However, having taken care of such risks in the regulated norms and laws, we still have to use and increase use of basically here the approach is again very obviously three-pronged. One is bio-based building blocks. Building blocks means basically either monomers for making polymers, or maybe minerals for making various pigments and fillers and extenders, because polymer on one hand and pigment and extender and filler on the other, these are the two main buckets of raw materials that a paint and coating industry uses. Okay, So, and then the bio-based solvents, because solvents mainly come from petrochemicals, you know. So definitely we are looking at bio-based solvents, like we are looking at, you know, biologically derived xylene, biologically derived MTO equivalent solvent, you know, etc., etc. And then the good part of researching on bio-based solvent is also that many of the solvents which we cannot use today because of EHS restrictions, for example, they may be either carcinogenic or mutagenic or reproductive. Sorry, I think the network connection was lost for a minute. So beautiful outcome of the research on bio-based solvents is that in place of CMR, meaning carcinogenic, mutagenic, reproductive toxin solvents, we have also started getting you know, non-CMR solvents. Of course, non-CMR solvents, I would also mention that they are not always necessarily from bio-based. Okay, even you know, synthetically made solvents, you know, solvent variants from CMR to non-CMR are also known. So I think instead of calling this sustainable solvents as only bio-based solvents, I think we should call them as more sustainable solvents. They can be either bio-based or they can be less, you know, toxic or less harmful. A nice example is, for example, all the formamide category solvent, you know, which you know that whether it is DMF, dimethyl formamide, dimethyl diethyl acetamide, etc., etc., they are all carcinogenic. Okay, and while they are extremely required for dissolving some of the very obstinate you know, materials, building blocks, like, you know, if you want to dissolve certain, you know, amide or urea or carbamate, etc., functionality containing molecules, you know, you mostly require this kind of solvents. For example, now there is a synthetic alternative that one of the global companies has come up with. Just for one example, you know, dibutyl, I think formamide or acetamide. Actually, I'm more conversant with the trade name of the solvent, Temizolve. Okay, so, and it's a beautiful solvent having almost equal polarity, little less, of course, because of the butyl groups, but almost equal cutting power for all those obstinate molecules which you want to dissolve in such formamide solvents. So that is also, now, in spite of being a non-bio based, in spite of being synthetic, you see that is also a very good sustainable alternative solvent. Okay, and then the third category is renewable additives. Like, for example, people used to use fumed silica a lot in coating and paints. You know, it's a very, very important ingredient for many purposes. Now, we all probably know that a very similar category of fumed silica has started coming from rice husk. Now, you see, here the beautiful benefit is that rice husk and husk from, maybe now the, you know, things have started coming from rice husk, maybe from many other crop plant husks also similar silica would gradually become available. Right now we are only getting supplies of rice husk silica in a commercial quantities. So that's a beautiful example of how, you know, sustainable additives we can get. Okay, sorry, anybody asking any question?
No, from participant, request to participant mute you.
Okay.
Madhu sir, please mute you.
Yeah, even the host can also mute him, no problem. Yeah, he may be, you know, he may not have noticed.
We will
has got unmuted.
Yeah.
So So there are various examples like that, and everything doesn't have to be really bio-based. Even synthetic alternatives can also be very, very sustainable, like I was saying. Now, next slide, please. Yeah. And then these are various other examples, like see, all the oils and fatty acids that we use for making alkyd chemistry, they are anyway all bio-based from the very beginning. Okay, and then even the glycerin also, to a great extent, glycerin is also actually available from the oils only. If you saponify an oil, you get glycerin. And even after the distillation of these vegetable oils, to get the pure quantity, whatever the bottom residue is there, generally, that's a mixture of acids and the oils. And when these bottom residues are also again saponified to get the complete free acids, you also get some glycerin from there. Of course, apart from that, there is synthetic glycerin as well, and glycerin also coming from petrochemical. So those things are called technical glycerin. So as you see, alkyd, which is one of the largest volume workhorse of the paint and coating industry, whichever kind of paint you want to make. Now, these alkyds have always been sustainable because, anything from 10, 20 to, up to 40%, by weight of the polymers can be oils and fats, in case of alkyds. Now, and then there are so-called non-green or non-sustainable polymers, acrylics and epoxies. These are the three other categories. If we talk about these three categories, then almost all categories of polymers are exhausted so far as paint and coating is concerned. Okay. Now, these epoxies and acrylics and polyesters are predominantly, directly from the fossil fuel route, so far as all their building blocks are concerned. Okay. Like I said, except for glycerin, all the polyacids and polyols, whether you take phthalic acid, terephthalic acid, isophthalic acid, or you take trimellitic anhydride, etc., on the acid part, and you take any of the glycols, like starting from the ethylene glycol, diethylene glycol, then trimethylol propane, and pentaerythritol, neopentyl glycol. These are all the well-known glycols used for polyesters. They're all from non-renewable and so-called non-sustainable sources. However, for some of them, for example, in pentaerythritol, good quantity of biologically derived pentaerythritol is also being produced and mixed along with the technical grade of penta by the most famous popular suppliers and manufacturers of penta, for example, whether it is First Stop or anybody else. So that route has become quite well known and also has come within the reaches of the economic viability and commercial viability. Because sometimes when you try to use renewable and biologically derived or other sustainable materials, many of the times they are not commercially viable. But there are some examples where commercial viability has come. And then otherwise, all these acrylics and epoxies and polyesters can also be modified to an extent by various, oils to an extent, so that there is the optimum balance of properties retained. Okay, so that way, at least partial renewable content and partial sustainability is also brought into these ranges of polymers as well. Okay. And bio-based solvent, yes, there are solvents being made from corn, sugar, and beet, and I also talked about a non-bio-based but sustainable solvent as well. These days, even some of the sugar-derived glycols are also attempted to bring in the arena of polyesters and uh, alkyds. For example, sorbitol. Okay, sorbitol was generally known to be a degrading material at high temperature, but people have perfected the art and science of making sorbitol a part of the polyester and alkyd backbone by now. Okay, so that also helps to increase the good amount of renewable content. Alkyd that may not be necessary from renewable point of view, but at the same time sorbitol is another very inexpensive raw material. So apart from the green part, it also brings down the cost, and when it brings down the cost, that also makes it sustainable for the customer. Okay. And then sorbitol has also been incorporated in polyester as well. And then, as I said, that recyclability is another good parameter of sustainability. For example, again, looking at the polyester industry, there is a huge quantity of end of use, waste polyethylene glycol, whether it is in the form of PET chips, which goes into packaging, or it is in the form of the staple PET fibers. Both kind of wastes are available in huge bulk quantity, and very standard methods and standard companies have come up, even in India, who are, collecting these wastes and accumulating them in commercially viable large quantities, washing them, purifying them, cleaning them, and then resupplying back to the industry of polymer and paints and coatings. And PET is another material which is very convenient to glycolize into very low molecular weight fragments, and then they can again go back into the into a new polyester or new alkyd backbone across industries, whether it is engineering thermoplastic, whether it is packaging, or whether it is textile, or whether it is paint and coating. So the recyclability attainment of polyethylene terephthalate is a very huge accomplishment of the polyester industry as a whole, irrespective of which kind of end products it is. In every kind of end product, it is gone. Then, even for packaging, how much can you use recyclable material? Now, good news is that most of the paint packaging is made with PET, either PET or crystalline polypropylene or polyethylene, depending on what kind of paint you are trying to package. Okay, and what kind of a package do you want? Now, paper bag is of course always there, which is anywhere sustainable, but that is only useful for certain types of materials, but not all. They are only useful for some solid dispersible polymers or putties or this kind of solid powdery materials. But for any liquid components, these are the type of things that are used: polypropylene, polyethylene, and PET, polyester. Now, polyester, I already said. Now, even in polyethylene, polypropylene, also controlled quantity of bioabsorbability, and which later on in the long run, because of bioabsorbability, then they finally become kind of liable to various type of enzymatic degradation when their particle size, etc., goes down very fine because of the bioabsorbability. So so what happens is that people are trying to incorporate degradable materials in such a way into polyethylene, polypropylene packaging that when the degradable material degrades, then the whole polyethylene, polypropylene physically disintegrates and it becomes absorbable into the soil instead of remaining on the surface of the soil. Now, when it becomes absorbable in the soil, there are two possible destinies. A, if there are certain microorganisms which can still eat upon them in the long run, or even if they are not a menace, because they gradually keep going below and below and below towards the center of the earth, and one day they will become part of the fossil fuel. So that bioabsorbability is also very important, not only bio-based. So that is also a good way of recycling, That recycling may not be, in the form of direct degradation into getting back some monomeric building blocks in hand, or not a recyclability into the hand of the consumer or the customer, but it is also a kind of recyclability wherein the material goes back to Mother Earth, in a form which does not destroy the surface of the earth. Yeah, next slide, please. Elimination of toxic ingredients. Yeah, I mean, the APEOs, alkyl phenol ethoxylate, is a classic example. We are trying to completely do away with alkyl phenol ethoxylates from the paint and coating industry. And, alkyl phenol ethoxylates are basically a kind of surfactants, which are very important. Yeah, somebody has raised a hand, please. So, admin may unmute him. Hemavati, ABPST. You want to ask any question?
Hemavati ma'am, you have any query? Maybe due to some
Maybe, yeah, maybe. Yeah.
later we
Else
can
we'll-
take that.
yeah.
Yeah.
So APEOs are part of very important surfactants, but then APEOs have been removed by very alkali, fatty alcohol ethoxylates a lot. And they're also very good surfactants, and in fact, they're now much, much more popular. And and their surfactancy efficiency is also as good as the APEOs. So APEOs are gradually becoming history. Now, in terms of polymers, particularly surfactants are required in emulsion polymers and any other water-soluble polymeric system, either water-soluble or water-suspendable polymeric systems. So from there, it is almost gone, unless, I mean, there are ample alternatives to APEOs available. For example, in Asian Paints, as far as polymer is concerned, we are now 100% free of APEOs. In any of our new polymeric design, we do not use them. Now from the paints, finally, which means polymers plus the pigments, extenders, and fillers, that is called a paint, right? Polymer paint is basically a liquid polymer composite, LPC. Now, in paints also, further surfactants are required for various purposes. Some of the APOs have globally remained as ingredients of paints, where exact equivalent performance has not been achieved by non-APOs. Much of it has been actually removed. Maybe 80% has been removed and 20% APOs have been there. But I believe, thanks to all the very innovative surfactant companies of Croda and others, very soon will be completely out of APEOs. Now, another thing is that APEOs are a little cheaper than non-APEOs. So therefore, in whichever areas, whichever jurisdictions of the world, APEOs are still allowed. Now some of the progressive companies may voluntarily get out of APEOs, but then some of the companies, because of cost and price benefit, may still use APEO. But I think when sufficient less expensive alternatives of APEOs will be there in the market, then nobody will like to use the APEOs anymore. And probably the governments of all countries will also be confident enough to bring regulations against APEOs. In some other countries it is there, in some other countries it is not there. Next slide, please. Next slide, please. Well, this, I think, recycling part we have spoken about. There is nothing much further to elaborate. We can keep on talking, but I think time is also important. So this can be skipped. Next slide, please. Alkyls we have spoken already. Next slide, please. Acrylics, already told you how acrylics can have certain renewable benefits. Sorry, just stay on the acrylic for a moment. Yeah, so I said that you can oil modify the acrylics to an extent. And apart from that, some monomers have also come. For example, itaconic acid and itaconic anhydride, etc. They are also from renewable resources, and so we can use them in the acrylics as well. and and people have also mastered the art of making adducts of some oils and fatty acids with some of the so-called non-renewable acrylate monomers, thereby making them maybe anything between 50 to 70% lesser carbon footprint. So that kind of monomers have also started coming in the acrylics. And there are also certain fatty acrylates also available. They're already available: stearyl, lauryl, etc., octyl, etc. They are acrylates and methacrylates. They are also used. So whenever they are used, that they bring the appropriate amount of lesser carbon footprint. Yeah, next please. Epoxy I have already spoken about. Apart from oil modification and oil-based enhancement of epoxies, the people have also been trying to get biologically derived alternatives in place of the basic building block of the epoxy resin, which is a reaction product of bisphenol A and epichlorohydrin. Okay, so basically what people are trying is that lots of these oils and fatty acids, their double bonds, their unsaturations are easily oxidized and converted to epoxy linkage oxirane rings. Okay, for example, you can have epoxidized soya fatty acid, epoxidized soya oil, epoxidized DCO, etc., etc. So they are also good sources of epoxy in the epoxy resins. However, you can understand BPA based epoxy is still the main workhorse in the epoxy resin because of structural strength that the BPA based epoxy provides because of the bisphenol unit in between, that is seldom available from any of the alternate source of glycidyl ring or the oxygen ring. Okay, so therefore, while all these more sustainable sources of epoxy are coming one after the other, as commercially available molecules, they can only complement various properties that we get from a typical BPA derived epoxy, BPA epoxy, and cannot actually replace it. Okay, that's how the situation is. Yeah, next please. Polyurethane. Polyurethane are basically made from all these acrylics and alkyds and polyesters only. So whenever you have any of these binders hydroxyl terminated, which is called a polymeric polyol, and then you react them with the appropriate dosage of isocyanates or polyisocyanates, you get the polyurethanes. Okay, so therefore, so long as you are able, or to the extent you are able to bring renewability or sustainability in those polymeric backbones, or reduce the carbon footprint in those polymeric backbones, you have also brought that much extent of sustainability in the urethanes. That's it, as simple as that. Yeah, next please. So that's the conclusion, that sustainable alternatives to traditional architectural, decorative, industrial and automotive coatings are increasingly being sought by the customers as well as the paint companies as well, and also the legislative authorities of the countries. The increased use of naturally derived raw materials in binder component of coatings can improve the sustainability. It is true, but of course, with a rider that we cannot make indiscriminately increased use of naturally derived raw materials, because we can actually deplete them much faster than we can deplete the fossil fuel based resources. Then re-engineering, which is part of the recycle and reuse, that is also very important. And then eco-friendly paint and coating manufacturers must strive to achieve sustainability goals while remaining competitive. So, like I said, that being commercially viable also very important. If so-called greener, more renewable or more sustainable building block of a polymer is extremely costly, then we cannot really sustain that. That doesn't really bring sustainability. However, I'll give you a very simple example ready in hand. See, the propylene glycol, which is 1,3-propanediol, it's another workhorse in the paint industry. It has got various uses. It has used as a building block of polymers. It is also used as a humectant, which retains water wherever is required in the paints. Okay, and it has various other uses also. Now there is a greener derivative of this 1,3, and then it can also become part of the polypropylene glycol. It can also become part of polyesters, etc., because it's a glycol. Now, a greener derivative, greener alternative of this is a 1,2. I'm sorry, the non-green was the traditional one is 1,2, not 1,3. Is the propylene glycol, where the second carbon is having a methyl derivative, methyl substitution, and the natural alternative or greener alternative is the 1,3, okay, which is a linear one. Okay, the 2-hydroxyl and the 2 extreme ends on 1 and 3 carbon. Now that 1,3,1, so far it has a lot of promises. So many of us are trying to create polymers and paint formulations by using this just to remain technology ready. But I don't think in the next 5 to 10 years will not be able to use this particular molecule in good quantity, because it is still not commercially viable. It is at least 6 times more costly than the propylene glycol. Okay, so unless now people have started using this in little bit quantity in solid polyurethanes and some water treatment chemicals, etc., which are something like, sometimes they are niche products, okay, where the company, the manufacturer as well as the customer can bear a little bit of cost impact. If the basic cost itself is very high, suppose you have a 700 rupees per kg material, and if you increase 20 rupees over there, it can be absorbed. But if you have a 200 rupees per kg material, and if you increase cost 20 rupees, that is not absorbable. So it's a classic example where we are making many things technology ready by using this greener alternative of propylene glycol, but I don't know, and we don't know collectively, when really we'll be able to make use of this greener alternative in as much quantity as we are using the propylene glycol today, and in as diverse applications as we are using propylene glycol today. So this commercial viability part is also very important. So that's kind of the last but not the least conclusion of any green and sustainability effort. Yeah, thank you very much. I think I overshot my time by almost 100%. I thought I will not have much material to talk because I was not getting time to prepare. But at the end, I think I ended up talking for almost maybe 1 hour, 15 minutes or something like that. So thanks so much for all the patience. Yeah.
And thank you so much, sir, for first of all accepting our invitation with the busy schedule and give us a wonderful lecture with a cutting edge technology and what happened in the real practical lab or practical industrial application. So now the forum is open. So if anybody have any query, they can ask.
Actually, sir, some question given in the chat box. Okay.
Okay. Let me try and open the chat box if I can. Okay. So what does the surfactants actually do in acrylic paints? Okay. So like I said, if I have to answer this question, in solvent-based acrylic paints, like for example, if you try to put, acrylic paints where you get the strong smell of solvent, if you can think, something that you may put as a wood lacquer, or some other lacquer on paint, etc. Their surfactants do not have much use. Something called dispersing agent is of course required, which is very close to surfactant while making that particular paint, because there also you have to disperse titanium dioxide and other ingredients, inorganic ingredients in the polymer. So to an extent that is required, but typical surfactants are required when you make water-based polymers and their paints, okay, which you typically as a consumer, you may be more conversant with the term called emulsion paints. For example, the paint that you put on your walls, your walls of your home, either interior walls or the exterior wall. So there, the polymer that you make, in any polymer you make, if you want to suspend or disperse in water, because polymers, with whatever polymer you make, generally have sufficient hydrophobicity to repel water to an extent. Some polymer may be a little more hydrophilic than others, but ultimately they don't want to dissolve in water. There are very few kinds of polymers. I can give example of that also, which readily dissolves in water. There are that kind also, but most polymers that we are generally conversant with, they are not soluble, not even dispersible in water very easily. So to make them, you need surfactants. That's the typical job of surfactants. I don't know whether I could satisfy the answer of the question. Then how do you prevent the sick building syndrome issue? What is that sick building syndrome issue? If the person asking the question could explain, I could attempt to answer. Maybe she can write on the chat box what does she mean. Meanwhile, I can go to the next question. Can you throw some details about conducting paints? See, conducting paints is a very niche category of thing. It is not so common. It is still quite fancy. We have also, they are more like inks. For example, you can make a conducting ink which can replace your electrical wear. Okay. So there are rather insulating paints a lot. Okay. Where you have to insulate either a high voltage, or you may have to insulate a high radiation. But generally, conducting paints are made in the forms of inks, to the extent of my knowledge. Okay, and yeah. So,
Hello, sir.
Yeah.
Yeah, I only asked that question. I'm also working polymer field only.
Yeah.
So we are trying to prepare some conducting material, especially the organic conducting polymers, and we wanted to mix it with paint and apply it.
What would be the objective, sir?
Objective will be in acrylic or in
Sorry?
epoxy. But our problem is that is not.
No.
The
I'm
prepared
saying,
polymer is not able to dissolve.
What would be the objective of making such paint as a customer?
That
For
is just
example, if you are buying that paint, for what purpose will you buy that conductive paint?
For EMI shielding, anti-static agent, something like that.
Yeah, so that is not completely a conducting paint. You can say that you have increased the or you have decreased the ohm resistivity to an extent, so that maybe either you may reduce the static effect, you can shield the radiation. I did talk about radiation shielding paint, but you would not typically call it a conducting paint. You might, because paints are generally insulators, Now you can either increase the insulation ability, that is increase the volume resistivity, or you can try to reduce the volume resistivity to an extent where at least the static charges are conducted. It is like earthing an electrical line, something like that. Am I correct, sir?
Yeah, you are right.
Yeah, so there you do not have the whole paint conductive, but you may have to incorporate certain conductive ingredients.
Yes, you are right. But once I apply that paint on the surface, but it is getting peeled off, it is coming out.
Yeah, you have to work on the adhesion property of the paint. So that will not that you will not be able to bring through the conductive additives that you are adding or the fillers that you are adding. You have to bring the adhesion. There are various adhesion promoters available which you can directly incorporate in your paint formulation depending on which substrate you are applying this paint. If you are applying on metal, then you have to deploy a different strategy vis-a-vis if you are applying on cement or concrete or wood. What is the substrate that you have to decide, and then you can even search the internet and get a lot of advices on adhesion promoter. If you can search by using this keyword, you can get a lot of adhesion promoters, and you have to select the right one depending on what type of paint it is. When I say what type, you have to understand whether it's an epoxy or an acrylic or what. Secondly, what is the type of substrate you are applying it. These two things you have to keep in mind while selecting the right adhesion promoter. The other approach is that if you are not kind of buying a paint and topping it up with your additive, but rather creating your own polymer and your own paint, then you can even go to the building block of the polymer and incorporate certain adhesion improving monomers into the polymer backbone. So that is another strategy. That strategy you can only apply if you are making the paint from very scratch. But if you're buying a regular paint and topping up with certain additives and fillers to make it conductive, then adhesion promoter is something that you have to work on. Yeah.
Okay. You are not working in that area, sir, in your Asian paints?
Adhesion promotion is an area where you have to work every day. But the thing is that what I will select depends a lot on actually working hands-on on the problem.
Yeah, actually, I'm coating on a metal.
No, I understand, but then we have to see what kind of failure is happening. You see, otherwise, anything that I say will not be different from what you get from the internet. You put this term adhesion promoter in coating, you will get hundreds and hundreds of reference. So I can also tell you one or two of them, but just by that will not be sufficient. Either you have to directly consult an expert, by giving him your paint in hand and telling him the recipe, then he might suggest what kind of adhesion promoter is required. Okay, the whole recipe will be required. Okay, to give you an advice. Yeah.
Okay.
If you give somebody a full recipe, then somebody may definitely be able to give you more specific advices on which adhesion promoter to be used.
Okay.
Hello, sir.
Yeah.
Sir, actually now the research is currently going on some photoluminescence paint. Okay. So my question is, what is the mechanism to get this kind of photoluminescence paint property? That means, is it related to the lifetime of the charge carrier, or also it's involved some metastable state into the materials that can actually accelerate the time of the charge carrier into the system?
See, as a paint formulator, I would rather look at it in a much more simpler way. There is a thing called cross-breeding of concepts, which is a much simpler way than always to go back to the drawing book or to the basic fundamentals. Now, if I know what are the chemicals used for a photochromatic lens of your spectacles, then I should simply translate that to make my photoluminescent paint. Just an example. Now, that may give you, let's say, a particular color. Okay, when you shine
Okay, sir.
light on it.
Light, yes.
Now, yeah, now let's say you want two different colors in two different situations. Okay, there are
Okay,
also treatments which are available which will give you two different or three different colors in different wavelengths of light that you shine it with. Or then you can also mix photoluminescence with some thermoluminescence or thermochromatism. Those kind of pigments are also available. Okay, so if you put it on your exterior wall, then apart from the light, even the heat can also work. So let's say you have two sets of different pigments. One is thermoluminescent, another is photoluminescent. Now, in the daytime, only the thermoluminescent additives may work and give you a certain color. Okay, and maybe a composite
yes, sir.
color, because both heat and light is available. Whereas
Okay.
in the night, when only the let's say heat and light both are not available, but if your wall is under a, let's say, a light that you are putting from your end, because lots of our building exterior also has the exposure to our society lights, street lights, etc., etc. You know, there you can get
Yes, sir.
only the scenario. So the point is that you don't have to always go back to the basic science to create a paint, because lots of those things have been already done in other industries and you can simply borrow from them.
Okay, okay, okay.
As far as paint is concerned, now if you want to say that I want to make a photoluminescent polymer, then what I would try to do is that I will see that, such photoluminescent groups anchored to my monomeric structure. If I want to make an acrylic, I would look for an acrylic backbone attached to a photoluminescent moiety, and I will try to use it in my backbone. So that way we would make our life simpler as developers.
And one question, sir, from my side, that I'm not take the name, but recently in ad, the commercial ad, some company that show that is a graphene paint. Graphene paint, they are make more shielding and more rough protection. So is this graphene means, that means we need to add that molecule, the material or 2D material into it, or it need to manufacture or synthesis in situ or during the chemical process of paint when we create it, or we just
See,
add that?
yeah, no, good question. See, the thing is that typical graphene is still synthesized by an highly acidic process. Okay, highly acidic oxidation followed by a reduction. Now that process nobody can make in situ in the paint. Okay, so there one has to use readily available graphene and mix it with the paint in various mechanisms. There can be various equipments by which you can mix, and you can get various functional performance and properties. Now there are other kind of graphenes which are little uh, different in terms of structure, which are called few layer graphene or multi-layer graphene instead of a single layer graphene, which can be made in a top-down process, meaning that you can, just like many of you may have heard about, intercalation and exfoliation of silicate clays, for example, right? So if clay is a two-dimensional,
Something network issue maybe.
What a connection to you.
Ah.
Lost connection for a
Yeah,
few moments. So what I was saying is that if the bentonite intercalated and exfoliated, then you can safely assume and expect that you will also be intercalate and exfoliate graphite, which is a cheaper carbon source, but have the same two-dimensional structure and maybe millions of layers or thousands of layers. Actually, graphene is made from graphite only, right? It is made by an acidic oxidation followed by reduction, but you can also make it, theoretically speaking, you can also make it by intercalation and exfoliation. Now, when I said theoretical, but actually practically it has been made. And we have also been able to demonstrate that we have also been able to make multi-layer or few layer graphenes directly from graphite by way of appropriate intercalation and exfoliation. Okay. Now, that is something which can be considered or at least attempted to be made in situ during the paint formulation. Not for every paint formulation, the kind of the exact specific paint which you have seen in the advertisement and which you will very soon see in the market, or it has actually started going to the market already. There, that paint is made in a particular process where this in situ intercalation exfoliation is not possible. But then suppose if for some other type of, I'm not telling that for intellectual property and confidentiality point of view, but you can imagine there are other types of industrial paints, which are made completely with different equipment, and not only different equipment, but a completely different chemistry. This emulsion paints are acrylic chemistry, but there are other chemistries of paint like we talked about, right? Polyester, alkyd, epoxy, etc., etc. In some of those chemistries, you can also make in situ the intercalation and exfoliation of graphite to convert into few layer or multi-layer of graphene. They will not be the ideal textbook single layer graphene, but they will still have few or multiple layers, up to 10 or 20 layers attached to it. But as you can imagine, compared to a million layer or couple of thousand layers, okay, 10 layer is how much of a difference. So this 10 layer material will have very similar properties, almost close to graphene in many aspects, may not be in every aspect. Okay, so that can be made in situ. And we have also developed that technology in-house, not in this particular paint whose advertisement you have seen, but in some other kind of industrial coatings.
And one more question related to that. That means when we are talking about the toughness or roughness of the paint, it means we are testing the property of that material, or we are testing after mixing that material, 2D material, not graphene, and also other material, and then we will test that property, or it will be property we are claiming, or they are claiming that before adding in the paint and in raw material as a raw materials property.
No, see, it is not that, let's say I say that I got this much of tensile property in my paint, or this kind of elastic modulus in my paint. That doesn't mean that the same value I should get in the graphene that I'm using. Now you put graphene in rubber, you will get one kind of one set of mechanical properties. You put graphene in acrylic emulsion, you will get one set of properties. You put graphene in a solvent-based acrylic, you get another set of properties. You put graphene in a polyester, you get another property. You put graphene in an epoxy, you get another property. You may have certain reactions also. So, see, so the structure property relationship between the raw material that you are using versus the paint are not so straightforward. However, there is always certain correlation which through knowledge and experience one has to draw. Now, if I am putting graphene into something, definitely I have certain expectation. Now, how do I set my expectation? That is definitely based on some knowledge and experience, and that is definitely not based on just random, trial.
Choice of,
However, what value I will end up with, I may have expectation around certain parameter of property. I may have expectation about tensile modulus. I may have expectation around elastic modulus. I may have expectation about conductivity, etc. But what value will reach, that I don't think anybody can predict or calculate or simulate. Yeah, I mean, with the advent of technology, one day that may be possible, but I don't think right now that is possible.
okay. Thank you so much, sir. And is anybody has any query?
So, thank you, sir.
So, may I stop your presentation, sir?
Yes.
Surely.
So, sir, thank you,
Okay.
sir, for your.
So thank
for
you
your
very much,
excellent-
also all of you.
Sir, thank you, sir, for your wonderful lecture, and we got a lot of information from you regarding the paints and coatings. So, as the formal
It is also my
procedure,
pleasure. Yeah.
yes. Sir, I would request you and all the participants, please switch on the video so that we can take a screenshot, which will be
A group photograph,
yes,
digital group photograph.
Okay.
So kindly switch on the video.
I think a lot of people have raised their hands or something. I don't know. Anyway.
Please switch on the video.
This is
Please
very nice.
do not post any message. So I am unable to take the screenshot. Please do not post any message.
For the timing, yeah.
Yes. So please switch on so that I can take a screenshot. So all the participants, please. Anindita Laha, Binoy Krishna, Dr. Saurav Ranjan sir, Madhu Shekhar, Ravi Kumar, please just switch on the video. Ravi Kumar.
And
So Anindita
you,
Laha,
sir.
Binoy Krishna, please
And
switch on the video.
thank
Deepti
you
Ghatak.
all. And thank you, sir.
Okay.
So thank you.
Camera not working.
Once again.
Okay, sir. Okay.
Okay. See you.
Now,
Bye.
sir.
So just to wait few minutes more,
Minutes.
sir.
Okay.
So
So now, actually, the program is going on the digital platform. So we have a digital memento. So from Dr. Sudhir Chandra Suri Institute of Technology and Sports Complex, Namgam JS Group. So now I would like to request Dr. Biswajit Das to share the digital memento for a small token of appreciation. And I request Dr. Jyotsna Shyamroy sir, so accept this digital memento.
I'm just
Sure.
presenting. Just a few minutes.
And I request all the participants not to leave. So we have some information for tomorrow, exam feedback, etc. for 5 minutes maximum after this digital memento sharing.
Yeah. So, sir, from our college, a small token of appreciation to you.
Thank you very much. Yeah. Thanks for
Yeah.
the nice appreciation.
And thank you so much for giving this wonderful lecture and accept our invitation.
Yeah,
And
it's
hope
my
we will
pleasure.
in future we'll definitely meet again and collaborate and work definitely something.
Sure.
Okay. Thank you, sir. Good night.
Good night.
Good night.
Good night.
Okay.
Have a good night, everybody.
Okay, sir.
Good night.
Good night, sir.
Good night.